An algorithm is a step-by-step method for accomplishing a distinct task. A data structure is a way of organizing data so that it can be accessed or modified efficiently. When programmers write a program, they plan which components of the code come first and which come later. Here, algorithms can help them have clarity and save time. Moreover, they require a well-organized way to store data that can be easily accessed to provide output as per user requirements. Data structures prove helpful in such cases. Java is a perfect example for demonstrating the usefulness of algorithms and data structures in improving the efficiency of a program. This course focuses on explaining all of the concepts pertaining to algorithms and data structures. Implementation of those concepts in Java can help students to understand their use in real-life scenarios. Each of the popular examples of algorithms, such as the bubble, quick, and merge sort, can help programmers relate the algorithms to familiar programming scenarios, such as arranging numbers in ascending or descending order, and so on. Moreover, detailed explanations of data structure examples, such as the binary tree, hash table, and graphs, will help students understand the improved efficiency of the program. The course introduces different algorithmic techniques in each lesson. It does this by describing example problems and providing appropriate Java implementations. The course is structured to first provide a base understanding of runtime complexity theory, and then gradually exposes the student to various methods and concepts relating to the subject. Each lesson is designed to build on the previous ones. In this course, we will define space and time complexities and express them using Big O notation. We will also describe various classic sorting algorithms. Then we'll proceed to fundamentals, where we'll explain the workings of basic and complex data structures. Then we'll recognize various algorithm design paradigms. Lastly, we'll focus on implementation, where we will apply string matching techniques. And then we'll implement different graph algorithms. This course has 6 lessons. Lesson 1 covers algorithms and complexities. Lesson 2 covers sorting algorithms and fundamental data structures. Lesson 3 will cover hash tables and binary search trees. In Lesson 4, we'll cover algorithm design patterns. Then we'll finish with Lesson 5, string matching algorithms, and Lesson 6, graphs, prime numbers, and complexity classes. An algorithm is a set of logical instructions intended to perform a particular task. Algorithms are everywhere nowadays. As a software developer, understanding the core principles of algorithms and data structures will enable you to make informed decisions on how to approach a particular problem. This is valid whether you're working in a bank, writing accounting software, or doing medical research data, mining genetic code. So how do we determine which is the right algorithm to use when more than one solution to a problem exists? In this lesson, we'll examine different types of algorithms and discuss how the performance varies in each. We'll also discuss what makes an algorithm more efficient than another algorithm, and how to express the complexity of each. This lesson has 3 topics. Topic A, we'll be developing our first algorithm. Topic B, we'll be measuring algorithmic complexity with Big O notation. And Topic C, we'll identify algorithms with different complexities. By the end of this lesson, you'll be able to define an algorithm with an example, you'll be able to measure algorithmic complexity, you'll be able to identify algorithms with different complexities, and you'll be able to access various examples with different runtime complexities. An algorithm can be seen as a roadmap or a set of instructions to accomplish a well-defined task. In this topic, we'll build a simple example of one such algorithm to help us get started. Number systems have different bases. Decimals and numbers with a base of 10 are what most of us are familiar with. Computers, on the other hand, use only ones and zeros, or binary. Let's try to write some code that converts binary numbers to decimals. Specifically, we want to develop an algorithm that accepts a string containing ones and zeros and returns an integer. Let's say we were building an algorithm for converting binary numbers to decimal. We can convert the binary string by following the following steps. First, we could start from the end of the string and process each character one at a time. The position of each digit in the binary string corresponds to a decimal number in a sequence. To generate this sequence, you can start from 1 and multiply by 2 every time. So 1, 2, 4, 8, and so on. Please look at the conversion sequence row of this table. More formally, this sequence is a geometric progression that starts at 1 and progresses in a common ratio of 2. We then apply the binary string as a mask on the sequence, as you can see in the binary string or mask row, which is the second row of this table. The result is a new sequence where the values are only kept if the corresponding position in the binary string has a value of 1, as shown in the result row of the table. After applying the mask, we just need to sum up the resulting numbers together. In this example, the resulting total is 22. This is our decimal number corresponding to the binary number 10110. As a note, to design our algorithm, it's important to realize that we don't need to store the entire conversion sequence. Since we are processing one binary digit at a time, starting from the back, we only need to use the conversion number corresponding to the binary position we are processing. What you see before you are two different methods for converting a binary to a decimal. The top is the convert to decimal method. We can use a single conversion variable instead of a sequence and initialize this variable to the value of 1. We then use a loop to iterate over the length of the binary string starting from the end. While iterating, if the digit at our current position is 1, we add the current conversion variable to the final result. We then simply double the current conversion variable and repeat. The second method is the convert to decimal alt. In this case, instead of doubling this variable at each iteration, we can simply use the geometric progression formula to generate any value in the conversion sequence. The formula is x equals ar to the I power, where a is the starting number in our sequence, this is 1, r is the common ratio, which is the value of 2 for our sequence, and I is the sequence position starting from 0. Algorithmic complexity is a way to describe the efficiency of an algorithm as a relation of its input. It can be used to describe various properties of our code, such as runtime speed or memory requirements. It's also a very important tool programmers should understand in order to write efficient software. In this topic, Topic B, we'll start by describing a scenario, introducing the topic, and then dive into the details of the various types of complexities and the different techniques used to measure them. Imagine if we were given the task of writing a piece of software for air traffic control. Specifically, if we were asked to write an algorithm that, in a predefined space and altitude, will ring out an alarm if any two aircraft get too close to each other. In our implementation, we can solve the problem by computing all possible distances between every pair of airplanes in our airspace and by keeping only the minimum distance between them. If this minimum distance is less than a certain threshold, our software should ring out an alarm. The following snippet of code shows this solution. Here, we have a function named minimum distance, which takes an argument of all planes. Then, we have a variable min distance that will equal the max value predefined. Now we have to loop through each of the airplanes. So, we'll have point P1 equal to an outer loop, and then we'll have an inner loop for point P2. So for each of the points of P1, we'll have to navigate and loop through all the points for P2. When we get into this inner loop, we'll have a variable d that will equal the distance between point P1 and P2. And if d is not equal to 0, if there's no distance, and d is less than the minimum distance, then the minimum distance will be equal to d, and we can return that minimum distance. When we double the number of planes, the time taken doesn't just double, but it skyrockets. For example, our algorithm takes 2.6 seconds, or 2,647 milliseconds, to finish when it's dealing with 16,000 planes. However, if we double the amount of planes to 32,000, the time it takes increases to 10.4 seconds, or 10,000 milliseconds, a fourfold increase. In the above figure, we plot the benchmark results in a chart. So what's going on here? Our algorithm is doing a lot of work due to the nested loop. For every plane point in its input, it's calculating the distance to every other plane. The results in N2 calculations, where N is the number of planes we are monitoring. We can say that our algorithm has a runtime performance of O, N2, read as big O of N squared. Alternatively, we can also call it the quadratic runtime performance. The algorithm is a slow solution for the closest pair problem. There exists a much more efficient solution that involves a divide and conquer technique. This class of algorithms is explored in detail in the second part of this course in Lesson 4, Algorithm Design Paradigms, where we present a faster solution to the closest pair problem. Increasing the input load on your code does not always mean that the resource consumption will also increase in a directly proportional manner. The relation between the input size of your problem and the resource usage, like CPU time, memory, and so on, is what this topic is all about. In the next section, we will see different types of these relations between the problem, the input size, and resource usage. To better understand algorithmic complexity, we can make use of an analogy. Imagine that we were to set different types of algorithms so that they compete against one another on a racetrack. However, there's a slight twist. The race course has no finish line. Since the race is infinite, the aim of the race is to surpass the other slower opponents over time and not to finish first. In this analogy, the racetrack distance is our algorithmic input. How far from the start we get after a certain amount of time represents the amount of work done by our code. Recall the quadratic method for measuring the closest pair of planes in the preceding section. In our fictitious race, the quadratic algorithm starts quite fast and is able to move quite a distance before it starts slowing down, similar to a runner that is getting tired and slowing down. The further it gets away from the start line, the slower it gets, although it never stops moving. Not only do the algorithms progress through the race at different speeds, but their way of moving varies from one type to another. We already mentioned that big O of n squared solutions slow down as they progress along the race. Well, how does this compare to the others? Another type of runner taking part in our imaginary race is the linear algorithm. Linear algorithms are described with the notation of big O of n. Their speed on our racetrack is constant. Think of them as an old reliable car moving at the same fixed speed. In real life, solutions that have a big O of n runtime complexity have a running performance that is directly proportional to the size of their input. This means, for example, that if you double the input size of a linear algorithm, the algorithm would also take about twice as long to finish. The efficiency of each algorithm is always evaluated in the long run. Given a big enough input, a linear algorithm will always perform better than a quadratic one. We can go much quicker than big O of n. Imagine that our algorithm is continually accelerating along the track instead of moving constantly. This is the opposite of quadratic runtime. Given enough distance, these solutions can get really fast. We say that these types of algorithms have a logarithmic complexity written as O log n. In real life, this means that the algorithm doesn't slow much as the size of the input increases. Again, it doesn't matter if at the start the algorithm performs slower than a linear one for a small input. As for a big enough input, a logarithmic solution will always outperform a linear one. But can we go even faster? It turns out that there is another complexity class of algorithms that performs even better. Picture a runner in our race who has the ability to teleport in constant time to any location along our infinite track. Even if the teleportation takes a long time, as long as it's constant and doesn't depend on the distance traveled, this type of runner will always beat any other. No matter how long the teleportation takes, given enough distance, the algorithm will always arrive there first. This is what is known as a constant runtime complexity, written as big O of 1. Solutions that belong to this complexity class will have a runtime independent of the input size given. A specific algorithm performs about 2 operations to solve a problem. However, the relation to its input is big O of n squared. Assuming each operation is a slow one, such as file access, and has a constant time of about 0.25 milliseconds, the time required to perform those operations will be shown in the table. We work out the timings with a variable time being equal to 0.25 times operations times n squared, where operations is the number of operations performed. In this example, it's equal to 2, n is the input size, and 0.25 is the time taken per operation. Our logarithmic algorithm performs about 400 operations. However, its relation to the input size is logarithmic. Although this algorithm is slower for a smaller input, it quickly overtakes the quadratic algorithm. You can notice that with a large enough input, the difference in performance is huge. In this case, we work out the timing using time being equal to 0.25 times operations times log n, with operations being equal to 400. In the previous section, we have seen how we can use the big O notation to measure the runtime performance to our algorithms in proportion to the input size. We have neither examined in detail what big O of n really means, nor have we considered the performance of our algorithm in relation to the type of input it's given. If you look at the following code snippet, the method accepts an array containing a string and searches for a match. If one is found, the index of the array is returned. We can determine the complexity of an algorithm by checking for duplicates in an array and considering the best and worst case performances. If we find the number of operations in the contains duplicates method you see before you, we can determine the best and worst case. There's no need to work out the algorithmic complexity in big O notation. We can assume that the inner loop would result in 8 operations every time it executes. For the outer loop, we can assume 4 operations. So when we try to achieve this, we have to determine the worst case, which is that we might execute the loop n times, or the array length. In the best case scenario, we only execute the inner loop twice. The best case is when the duplicate numbers are in the front of the input array. The worst would be when the array doesn't contain any duplicates at all. So the worst case is when the array doesn't contain duplicates and is of size n. For the outer loop, we have 4 times n operations. For the inner loop, we'll have n times 8 operations. In total, we would have 4n plus 8n squared operations. There are 2 simple rules to follow when we want to express an algorithm using the big O notation. In this section, we will understand how to convert the expression from 4n plus 8n squared to the big O notation equivalent. The first rule to follow is to drop any constants. For example, 3n plus 4 becomes n, and a single constant, such as 5, becomes 1. If an algorithm simply has 4 constant instructions that don't depend on the input, we say that algorithm is big O of 1, also known as constant time complexity. The second rule is to drop everything except the highest order. Consider an algorithm that performs n plus n squared plus n to the third. The highest order variable of this is the n to the third part. If we keep the highest order, we end up with big O runtime complexity of big O of n to the third. In this topic, Topic C, identifying algorithms with different complexities, we shall look into examples of different complexities. This is important so that we can learn to recognize algorithms that belong to different complexity classes and possibly attempt improving the performance of each. Linear algorithms are the ones where the work done varies in direct proportion with the input size. That is, if you double the input size, you double the work done. These typically involve a single pass through the input. The problem presented in this example is that of counting the number of occurrences of a particular character in a string. Imagine we are given the string Sally sells seashells on the seashore, and we want to find out the number of occurrences of the letter A. In the code snippet you see before you, the count_chars method goes through each character in the input string, and if the character at the current position matches the search letter, a counter is increased. At the end of the loop, the final count is returned. Now, this algorithm is linear because its runtime is directly proportional to the string length. If we take the string length to be n, the runtime complexity of this Java method would be big O of n. Notice the single loop varying according to the input size. This is very typical of linear runtime complexity algorithms, where a constant number of operations are performed for each input unit. The input unit, in this example, is each character in the string. Quadratic complexity algorithms are not very performant for large input sizes. The work done increases following a quadratic proportion as we increase our input size. We already saw an example of big O of n squared in our minimum distance solution. The problem here in this example is about finding common elements contained in the 2 arrays, assuming no duplicate values exist in each array, producing the intersection of the 2 inputs. This results in a runtime complexity of big O of m times n, where m and n are the sizes of the first and second input arrays. If the input arrays are the same as n elements, this results in a runtime of big O of n squared. This can be demonstrated by the code you see before you. This is very much like a dictionary, or searching for a word in that dictionary. Since the dictionary is sorted, we can find the word we're looking for much quicker if the words were listed randomly. Logarithmic complexity algorithms are very fast, and their performance hardly degrades as you increase the problem size. These types of algorithms scale really well. Code that has a runtime complexity of big O of log n is usually recognizable since it systematically divides the input in several steps. Common examples that operate in logarithmic times are database indexes and binary trees. If we want to find an item in a list, we can do it much more efficiently if the input list is stored in some specific order. We can then use this ordering by jumping to specific positions of our list and skipping over a number of elements. In the binary search method you see before you, the method uses 3 array pointers: a start, an end, and a midpoint. The algorithm starts by checking the middle element of the array. If the element is not found and is less than the value at the middle, we choose to search in the lower half. Otherwise, we choose the upper half. Of note here, a lot of cryptographic techniques rely on the fact that no known polynomial time algorithm is known for prime factorization. However, nobody has yet proved that one doesn't exist. Hence, if a fast technique to find prime factors is ever discovered, many of the current encryption strategies will need to be reworked. As we have seen previously, algorithms that have an exponential runtime complexity scale really poorly. There are many examples of problems for which only a big O of k to the n power solution is known. Improving these algorithms is a very dynamic area of study in computer science. Examples of these include the traveling salesman problem and cracking a password using a brute force approach. Now let's look at an example of such a problem. A prime number is only divisible by itself in 1. The example problem we present here is called the prime factorization problem. It turns out that if you have the right set of prime numbers, you can create any other possible number by multiplying them all together. The problem is to find out these prime numbers. More specifically, given an integer input, finding all the prime numbers that are factors of the input. Those are primes that when multiplied together give us the input. The code you see before you shows one implementation for this problem called trail division. If we take an input decimal number of n digits, this algorithm would perform in big O of 10 to the n in the worst case. The algorithm works by using a counter, start at 2, and checks whether it's a factor of the input. This check is done by using the modulus operator. If the modulus operator leaves no remainder, then the value of the counter is a factor and is added to the factor list. The input is then divided by this factor. If the counter is not a factor, because the modulus leaves a remainder, then the counter is incremented by 1. This continues until x is reduced to 1. Now, if we try the code in front of you with 2 long numbers, it takes a really long time to run. The worst case of the algorithm is when the input is a prime number, wherein it needs to sequentially count all the way up to the prime number. This is what happens to the second input in this case. On the other hand, the large prime factor for the first input is only 10,973. So the algorithm only needs to count up to this, which it can do pretty quickly. Exponential complexity algorithms are usually best avoided, and an alternate solution should be investigated. This is due to its really bad scaling with the input size. This is not to say that these types of algorithms are useless. They may be suitable if the input size is small enough, or if it's guaranteed not to hit the worst case. Try running this program and see what I mean. The efficiency of constant runtime algorithms remains fixed as we increase the input size. Many examples of these exist. Consider, for example, accessing an element in an array. Access performance doesn't depend on the size of the array, so as we increase the size of the array, the access speed stays constant. Consider the following code. The number of operations performed remains constant, irrespective of the size of the input radius. Such an algorithm is said to have a runtime complexity of big O of 1. Constant complexity algorithms are the most desirable out of all the complexity classes for the best scaling. Many of the simple mathematical functions, such as finding the distance between 2 points and mapping a 3-dimensional coordinate to a 2-dimensional one, all fall under this class. In this lesson, we gave an introduction to algorithmic complexity and the notation to describe it. We have shown you how big O notation can be used to describe how well an algorithm scales as the input gets bigger. We have also seen various examples of complexity and shown you how you can intuitively differentiate between them. Lastly, understanding big O notation comes in handy when you need to design and implement new solutions or when you are diagnosing performance issues. In the previous lesson, we saw how the intersection problem can be improved by using a sorting algorithm. This is common with many problems. If the data is organized in an ordered manner, a more efficient algorithm can be developed. In this lesson, we'll start by exploring 3 types of sorting techniques, which are bubble, quick, and merge sorting. Later, we will learn different ways to organize data using fundamental data structures. This lesson has 4 topics. Topic A, introducing bubble sorting. Topic B, understanding quicksort. Topic C, using merge sort. And lastly, Topic D, getting started with fundamental data structures. By the end of this lesson, you'll be able to describe how bubble sorting works. You'll be able to implement faster sorting with the quicksort. You'll be able to characterize merge sorting. You'll be able to build a linked list data structure. You'll understand how to implement queues. And lastly, you'll be able to describe the stacked data structure. Now let's dive into Topic A, which introduces bubble sorting. Bubble sorting is the simplest sorting algorithm out there. The technique involves making multiple passes over the input array and swapping unordered elements close to one another. The technique is called bubble sort as the sorted list bubbles up from the tail end of the list. Bubble sorting is the simplest sorting algorithm out there. The technique involves making multiple passes over the input array and swapping unordered elements close to one another. The technique is called bubble sort as the sorted list bubbles up from the tail end of the list. All sorting algorithms accept a list of elements and then return them ordered. The main difference between each algorithm is the manner in which the sorting is done. Bubble sorting works by swapping adjacent elements. This pushes the sorted elements toward the end of the list. In the commented code at the top of this script, you see the pseudocode for bubble sort. The algorithm involves 3 simple tasks, which involves repeatedly stepping through the list to sort, comparing adjacent elements, and swapping them around if the first element is bigger than the second. How many passes do we need to perform on the array until our list is sorted? Well, it turns out that to guarantee that our list is sorted, we need to do n-1 passes on the list, n being the length of our array. We will show why n-1 passes are needed in the next section, but this is the main reason why bubble sort has a runtime complexity of big O of n squared, since we're processing n elements for n-1 times. Of note, the swap function in this pseudocode switches the values of the 2 array pointers j and j+1 using a temporary variable. If we want to implement the bubble sort in Java, we can look at the sort method you see before you. The tricky part of this algorithm is the swapping logic. This is done by assigning one of the elements to be swapped to a temporary variable, as you see in the sort method, where there is a temp var, which is an integer, which equals the numbers plus j being the controlling variable in the inner loop. Then we can create our numbers var j to be equal to j+1, and then once again take numbers j+1 to be equal to the temp var. So that's the swap and the bubble sort. There are 2 main techniques we can adopt to improve the performance of bubble sort. It's important to realize that although both of these strategies improve the overall performance of bubble sort in the average case, in the worst case the algorithm still has the same poor runtime complexity of big O of n squared. The first small enhancement we can make to the original bubble sort is make use of the fact that the sorted bubble is building at the end of the list. With every pass we make, another item is added at the end portion of this bubble. This is the reason why n-1 passes are needed. This is also shown in the figure. In this diagram, the items shown in the dotted circle are already sorted in the correct place. Although bubble sort is very easy to implement, it's one of the slowest sorting methods out there, but it can be improved. There are 2 main techniques we can adopt to improve the performance of bubble sort. It's important to realize that although both of these strategies improve the overall performance of bubble sort in the average case, in the worst case the algorithm still has the same poor runtime complexity of big O of n squared. The first small enhancement we can make to the original bubble sort is to make use of the fact that a sorted bubble is building at the end of the list. With every pass we make, another item is added at the end portion of this bubble. This is the reason why n-1 passes are needed. We can use this fact so we don't try to sort the elements inside this bubble. We can do this by slightly modifying our Java code, as shown in the method sort improvement 1. In the inner loop, instead of processing until the end of the list, we can stop just before the sorted bubble until numbers.length minus I. For brevity, we've replaced the swap logic with the sort improvement 1 method. If we give a sorted list to our bubble sort algorithm, we will still make multiple passes on it without modifying it. We can further improve the algorithm by cutting short the outer loop when the list inside the array is fully sorted. We can check that the array is sorted by checking if any swaps were done during our last pass. In this manner, if we give our method an already sorted list, we just need to do one pass on the array and leave it untouched. This means that the best case is now big O of n, although the worst case remains the same. We can improve the bubble sorting algorithm further by reducing the number of passes. If we change the bubble sort method so that it stops sorting if the array is untouched after an inner loop pass, we'll improve it. That solution can be developed easily if the outer for loop is changed into a while loop, and a flag is kept to indicate if any elements have been swapped while going through the array. This is shown in the sort improvement 2 method you see before you. Now let's dive into topic B, understanding quicksort. Algorithm complexity is a way to describe the efficiency of an algorithm as a relation of its input. It can be used to describe various properties of our code, such as runtime speed or memory requirements. It's also a very important tool programmers should understand to write efficient software. In this topic, we'll start by describing a scenario, introducing the topic, and then dive into the details of the various types of complexities and the different techniques used to measure them. Quicksort is a big improvement over bubble sort. This sorting technique was developed by British computer scientist Tony Hoare. The algorithm works in 3 main steps. First, we select a pivot. Then, we partition the list so that the elements on the left of the pivot are less than the value of the pivot and the ones on the right are greater. Lastly, we repeat steps 1 and 2 on the left and right parts separately. Since recursion is required for quicksort, we'll begin this topic by giving an example of recursion. Later, we'll see how the partitioning and the quicksort algorithm works, and in the end, we'll put the recursion techniques to use in the final part. Recursion is a really useful tool for algorithm designers. It allows us to solve large problems by solving a smaller occurrence of the same problem. Recursive functions usually have a common structure with the following components. 1 or more stopping conditions. Under certain conditions, it would stop the function from calling itself again. 1 or more recursive calls. This is when a function or method calls itself. In the next example, we will pick the binary search problem seen in the previous lesson and change the algorithm to work in a recursive manner. Recursion is a really useful tool for algorithm designers. It allows you to solve large problems by solving a smaller occurrence of the same problem. Recursive functions usually have a common structure with the following components. They have 1 or more stopping conditions. Under certain conditions, it would stop the function from calling itself again. They also have 1 or more recursive calls. This is when a function or method calls itself. In this example, we're showing you a binary search problem seen in a previous lesson, and we're changing the algorithm to work in a recursive manner. When we consider the binary search problem discussed in Lesson 1, Algorithms and Complexities, the implementation was iterative. It looped until an item is found or the end parameter is equal or greater than the start variable. The pseudocode you see in front of you in the comments is binary search. It actually has 2 stopping conditions. The function stops the recursive chain if it either finds the search item at the midpoint or if the start array pointer is greater than the end, meaning the item wasn't found. The stopping condition can easily be found by examining any return paths that don't involve further recursive calls. If we want to implement a binary search recursively and use the pseudocode we saw in the previous example, we can provide another method with a signature that only contains the search item and the sorted array as input. This method will then call the recursive function with the appropriate values, which you see on your screen with the binary search method that takes an integer x and an array of integer of sorted numbers. The Boolean search method shows the additional method for making the initial call and the recursive function. Of note, the original Hoare scheme performs better as it does fewer swaps, although it also suffers from slow performance when a sorted list is used as input. Both the Lomuto and Hoare schemes result in non-stable sorting. A stable sort means that if 2 or more elements have the same key value, they will appear in the same input order as the sorted output. There are other schemes that can be used to make quicksort stable, but they utilize more memory. Partitioning is the process by which we reorder our array so that the elements with a value less than our pivot are moved to the left of the pivot and those with a larger value are moved to the right. There are numerous manners in which we can do this. Here we will describe an easy-to-understand scheme known as Lomuto partitioning. Please take a look at this diagram. Before, we see the pivot all the way to the right. Then we move it in between so that it's neither to the highest or lowest element, and that's our pivot. One thing of note, many other schemes exist. The Lomuto scheme has the drawback that it's not very performant when it's used on already sorted lists. The original Hoare partition scheme we just learned performs better and works by having the array processed from both ends. To get a good perception on this partitioning scheme, it is best to simplify what the algorithm is doing in 5 simple steps as follows. First, we'll pick the rightmost element of the array as the pivot. Then, we'll start from the left and find the next element that is larger than that pivot. We'll then swap this element with the next, which is smaller than the pivot element. Then we'll repeat steps 2 and 3 until no more swapping is possible. Lastly, we'll swap the first item, which is larger than the pivot's value, with the pivot itself. In the partition method you see before you, we make use of 2 pointers, one pointing to the first item larger than the pivot value, and the other used to search for the value that is smaller than the pivot value. These are the integers named x and I, respectively. The algorithm starts by choosing the pivot as the last item on the input array. It then processes the array from left to right in a single pass using the variable I. If the element currently being processed at I is smaller than the pivot, x is then incremented and swapped. Using this technique, variable x is either pointing to a value larger than the pivot, or the value of x is the same as I, in which case swapping will not modify the array. Once the loop exists, we perform the final step of swapping the first item that is larger than the pivot's value with the pivot. This is exhibited in the partition method you see before you. The quicksort is from a class of algorithms called divide and conquer. We will see many other examples from this class in the course, and we will go into detail on divide and conquer in Lesson 4, Algorithm Design Paradigms. For now, it's important to know that divide and conquer algorithms keep on splitting the problem into smaller ones until the problem is small enough that it becomes trivial to solve. This splitting can be easily implemented using recursion. In quicksorting, we keep on recursively partitioning the array in this manner until the problem is small enough that we can easily solve it. When the array has only one element, the solution is simple. The array stays exactly as it is, as there is nothing to sort. This is the stopping condition of our recursive algorithm. When the array is larger than one element, we can keep dividing our array and using the partitioning method we developed in the previous section. The following code snippet shows the pseudocode for the complete quicksort. Just like most recursive functions, the code starts by checking the stopping condition. In this case, we'll check to see if the array has at least 2 elements by ensuring that the start array pointer is less than the end. This pseudocode is as follows. When we have at least 2 elements in the array, we call the partitioning method. Then, using the pivot's last position, which was returned by the partitioning method, we recursively quicksort the left part and then the right part. This is done by calling the same quicksort code using pointers of start and p-1, and then p+1, and then the end, not including the p, which is the pivot's position. Note that the trick to understanding how quicksort works is to realize that once we perform the partition call on the array, the element at the returned position, the pivot, doesn't need to move within the array anymore. This is because all the elements on its right are larger and the ones on the left are smaller, so the pivot is in the correct final position. If you look at the second sort method, this is the code for the complete quicksort. Just like most recursive functions, the code starts by checking the stopping condition. In this case, we check if the array has at least 2 elements by ensuring that the start array pointer is less than the end. When we have at least 2 elements in the array, we call the partitioning method. Then, using the pivot's last position, returned by the partitioning method, we recursively quicksort the left part and then the right part. This is done by calling the same quicksort code using pointers of start and p-1 and p+1 and end, not including the p, which is the pivot's position. Now it's time for topic C, using merge sort. Although the quicksort on average is pretty fast, it still has the theoretical worst time complexity of big O of n squared. In this topic, we shall examine another sorting algorithm, called merge sort, in which the worst time complexity is big O to n log n. Similar to quicksort, merge sort belongs to the divide and conquer class of algorithms. Merge sort can be summarized in 3 simple steps as follows. First, split the array in the middle. Second, recursively sort each part separately. And 3, merge the 2 sorted parts together. In the following section, we'll develop the preceding steps gradually, at each turn slowly building our understanding of how merge sorting works. One note is that although merge sort is theoretically faster than quicksort, in practice, Some implementations of quicksort can be more efficient than merge sort. Additionally, the merge sort uses about big O of n memory as opposed to quicksort, which is big O of log n. In the preceding section, we saw how we can use a recursive technique to split the problem into smaller multiple ones until the solution becomes easy to solve. Merge sort uses the same approach. The base case for our recursive technique is the same as quicksort. This is when the array is only one element long. When the array to sort only contains one item, the array is already sorted. The figure shows how merge sort array splitting occurs. At each step, we find the midpoint of the array and split the array in two. We then recursively sort the left and right part of the split array separately. We can stop the recursive call once the total elements to sort is equal to 1 as shown in the figure. If you take a look at the pseudocode for merge sort in its Java implementation in front of you, you'll notice this algorithm is from the same class of algorithms as quicksort. However, its runtime and space complexity are different. Instead of dividing the array from the pivot's position, the merge sort always partitions the array at the midpoint. This is a similar process to binary sort and results in log 2n array divisions. So how do we merge two sorted lists into a sorted one? Well, this is the task of the merge function, which is found at the end of the pseudocode shown in the preceding section. This process is shown in the figure. Merging two sorted lists is an easier task than sorting from scratch. This is similar to the intersection problem we saw in Lesson 1, Algorithms and Complexities. We can merge in linear time utilizing just 2 pointers and an empty array as shown in this diagram. The code for merging is shown in the highlighted code snippet. In this code, the system array copy function simply takes in a source array as a first argument and copies it to the target array, the second argument. It makes use of the start variable as a pointer, indicating where to place the first element of the source array onto the target one. In the merging part of the merge sort, we create a temporary array which is of size equal to the size of two array parts together. We then do a single pass in this array, filling the temporary array one item at a time by picking the smallest item between the two input lists, represented by the start, middle, and end pointers. After picking an item from one of the lists, we advance the pointer of that list and repeat until the merge is complete. Merge sort is theoretically one of the fastest sorting algorithms. The drawback of its speed is that it consumes a bit more memory, although some implementations exist that perform the merge step in place to save memory. For comparison, we present multiple sorting techniques with their runtime and memory performances in the following table. Now it's time for our fourth topic. Topic D, getting started with fundamental data structures. Data structures are a way to organize data so that the data is efficiently accessible for the problem we are trying to solve. Choosing the right data structure will depend on the type of problem we're trying to solve, the amount of data we need to organize, and the medium we use to store our data, like memory, disk, and so on. We have already seen and used one example of a data structure. In the preceding topics, we've made extensive use of arrays. Arrays are the most primitive of data structures. They provide access to our data using an index and are fixed and sized, also called static. This is opposed to other dynamic data structures that can grow and make more space for data whenever it's needed. More formally, a data structure is an organization of data elements, a collection of functions that can be applied on the data. Think about add, delete, and search functions, and any relations between the different data elements. This table shows common operations that some data structures provide, like search, add, size, update, delete, minimum, and maximum. In this topic, we will see various types of dynamic data structures. We will start with linked lists, which are optimized for dynamic growth but are slow while searching. Then we'll use these linked lists to implement other data structures on top, such as queues and stacks. A linked list is a list of data items where each item only knows about the next item in the list if there is one. The figure shows one such example. Each box in the figure represents a container for a data item we need to store. This container, called a node, contains our data values and a pointer to the next node in the list. As the diagram shows, the node on the front of the list is called the head of the list, and the last item of the list is called the tail. Separate pointers to these nodes are stored for easy access to the data structure. The advantage of using a linked list as opposed to an array is that a linked list can grow dynamically. When using an array, you allocate space in the start, and that space remains fixed. If you allocate too much and the space remains unused, you're wasting resources. On the other hand, if you make your array too small, the data might not fit. In a linked list, however, the space is not fixed. The structure grows dynamically as you add more data, and it shrinks, freeing memory space as you remove it. A linked list is a list of data items where each item only knows about the next item in the list if there is one. The advantage of using a linked list as opposed to an array is that a linked list can grow dynamically. When using an array, you allocate space in the start, and that space remains fixed. If you allocate too much and the space remains unused, you're wasting your resources. On the other hand, if you make your array too small, the data might not fit. In a linked list, however, the space is not fixed. The structure grows dynamically, and as you add more data, and it shrinks, freeing memory space as you remove it. We can model a linked list using separate node instances that are connected together to build our linked list. The linked list node method you see in front of you shows this. The class contains a self-reference so that we can link multiple nodes in list fashion. Notice how we use Java's optional classes instead of returning null pointers to represent whether there is a link to the next node. The tail node of a linked list will always have an empty optional. We also make use of generics to model the type of data we want to store. This way, we can keep the structure as general as possible so that it can be used by any data type. We can modify the Java node class to support the doubly linked list structure. A doubly linked list is a linked list in which each node contains a relation to the following and previous nodes. If we take a look at the code before us, we can see that the head node will have a null previous pointer, while the tail node will have a null next pointer. Before we can use any linked list operations, we need to initialize the data structure and mark it as empty. Conceptually, this is when the head of the list is pointing to nothing. We can do this in Java by adding this logic in a constructor. The code snippet you see before you, the public class linked list, shows this. Note, once again, we use generics to hold the type of items we want to store in the linked list. But how can we remove and add items from the head of the list? Well, if we add a node in a linked list, we require a two-pointer assignment. On the new node, you set the next pointer to point to whatever the head pointer is assigned to. Then you set the head pointer to point to this newly created node. So how can we add and remove items from the head of the list? Adding a node in a linked list requires a two-pointer reassignment. On the new node, you set the next pointer to point to whatever the head pointer is assigned to. Then, you set the head pointer to point to this newly created node. This process is shown in the figure. Deleting from the front of the list is the reverse. You set the head pointer to point to the next pointer of the node at the old head. For completeness, you can set this next pointer to point to nothing. To locate an item in a list, we need to traverse the entire list until we find the item we're searching or reach the end of the list. This can be done easily by starting at the head pointer and always following the node's next pointer until you either find the node with the value you're looking for or you run out of nodes. For example, the next pointer is a null one. The code you see before you shows the add front and delete front operations for a linked list. For the add front method, we simply create a new node with its next pointer set as the current head pointer. Then we assign the head to the new node. Notice in the delete method how we make use of Java's optional objects. If the head pointer is null, it will stay null and we don't change anything. Otherwise, we flatten it to the next pointer. Finally, we set the first node's pointer as null. The last step is not necessary since the orphaned node will be garbage collected. However, we're including it for completeness. Queues are abstract data structures that are meant to emulate the workings of real-life queues. They are used extensively in various applications such as resource allocation, scheduling, sorting, and many others. They are typically implemented using a double linked list, although many other implementations exist. A queue usually consists of two operations, an enqueue operation, where items are added to the rear of the queue, and an opposite dequeue operation, where items are removed from the front of the queue. These two operations make the mode of operation of this data structure called first in, first out, or FIFO. We can implement an efficient queue using a double linked list. This enables us to implement the dequeue operation by removing an item from the head of the linked list. Enqueue is simply adding an item to the tail of the linked list. This figure shows how the two operations are performed. The highlighted code shows one way to implement a find method. Again, observe how we make use of Java's optional methods. We start a while loop from the head pointer and keep on moving to the next node as long as there is a node present and that node doesn't contain the item we're looking for. We then return the last pointer, which can be an empty optional or a node containing a match. We can implement an efficient queue using a double linked list. This enables us to implement the dequeue operation by removing an item from the head of the linked list. NQ is simply adding an item to the tail of the linked list. In order to dequeue an item, we need to use a double linked list as a base data structure, and we'll need to just move the head to the next item in the list and unlink the old head by pointing the previous pointer to nothing. NQing at the tail is a three-step process. We'll point the new node's preceding pointer to the current tail, then point the current tail's next pointer to the new node. And finally, we'll move the tail to the new node. The following highlighted snippets show this in action. Stacks, typically also implemented using linked lists, work differently than queues. Instead of FIFO, first in, first out ordering, they have a last in, first out LIFO ordering. They have two main operations called push, which adds an item on top of the stack, and pop, which removes and returns one item from the top of the stack. Like queues, stacks are heavily used in many algorithms, such as depth-first search traversal, expression evaluations, and many others. To model a stack, it's enough to use a simple linked list. The head of the linked list can be used to reference the top of the stack. Every time we need to push something on the top of their stack, we can use the add front method we developed in the preceding sections. The implementations differ only in the fact that the pop operation returns the optional item on the top of the stack. Both push and pop can be seen in the Java implementation in the following code snippet. Notice how the pop operations will return an optional value, which is populated if the stack is not empty. The following code snippet shows the pseudocode for the complete quicksort using the implementation of the push and pop methods. Just like most recursive functions, the code starts by checking the stopping condition. In this case, we check if the array has at least two elements by ensuring that the start array pointer is less than the end. When we have at least two elements in the array, we call the partitioning method. Then, using the pivot's last position, which is returned by the partitioning method, we recursively quicksort the left part and then the right part. This is done by calling the same quicksort code using the pointers of start and p-1 and then p+1 and end, not including the p, which is the pivot's position. Note that the trick to understanding how quicksort works is to realize that once we perform the partition call on the array, the element at the return position, or the pivot, doesn't need to move within the array anymore. This is because all of the elements on its right are larger and the ones on the left are smaller. So the pivot is in the correct final position. In the highlighted block in front of you, we're using the stack data structure to reverse a string. So in order to do this, we need to push each character of the input string and then pop everything out one at a time, building a reverse string. As you can see, our signature is public string reverse, and we'll pass a string into it. Inside this method, you see that we are actually pushing each character of the input and then popping everything out one at a time. Stacks and queues don't necessarily need to be dynamic. You may want a more concise implementation if you know your data requirements are of a fixed size. Using an array approach to model stacks and queues guarantees that your data structure will only grow up to a certain size. The other advantage of using an array is that the array approach is more memory efficient if you can live with having a static data structure. The catch with static data structures is that the queue or stack can only grow to a maximum fixed size of your initially allocated array. The following code shows the process. Implementing a stack using an array involves first initializing an empty array with a fixed size. Then it's a matter of keeping an index pointer to the top of the stack, initially pointing to 0. As we push items on the stack, we place the item at this index and increment the pointer by 1. When we need to pop an element, we reduce this pointer by 1 and read the value. The process is shown in this code. Implementing a queue using an array requires a little more thinking. The difficulty with a queue is that the structure is modified from both ends, since it grows from the tail and shrinks from the head. As we enqueue and dequeue the contents of the queue, it seems to be moving towards the right of the array. We need to deal with what happens when the contents reaches the end of our array. To make the queue work in an array, we just need to let our data wrap around the edges, something like Pac-Man. When we reach the end of our array, we can just start again from the beginning index. This wraparound mechanism is called a circular buffer. It can be implemented using the modulus operator to access any element in the underlying array. The following code snippet shows how this works. Notice that when we enqueue an item, we place it at the tail position and increment the tail pointer using the mod operator. When the pointer is larger or equal to the size of the array, it wraps around and starts again from 0. The same happens on the DQ method, where we access and increment the head pointer in a similar fashion. The following code demonstrates this. In this highlighted code, we've written a safe and queue method that will fail when the queue is full. The idea is to return a Boolean value which is false when the queue is full and cannot accept further arguments. If we look at the code, we see that if there is no full, only at that point would we actually modify the array tail pointer. And we see the tail pointer will equal the tail pointer plus 1 modulus the actual length of the array, and then it would return true. But the safe and queue part of this is the return of the false if it is not full. We've now seen both queues and stacks that can be implemented using a static array structure instead of using the dynamic linked list. This has the advantage of consuming less memory per element, as a linked list has to store pointers to other nodes. However, this comes at the cost of having a limit on the structure size. In this lesson, we laid the foundations for the more complex upcoming topics. In the first few topics, we saw how a simple problem such as sorting can have many solutions, all with different performance properties. We explored 3 main implementations, which were bubble, quick, and merge sort. In later topics, we introduced data structures and studied various implementations and use cases of linked lists, queues, and stacks. We also saw how some data structures can be used as building blocks to build more complex ones on top. In the next lesson, we will study hash tables and binary trees, 2 important and widely used data structures. Now it's time for Lesson 3, Hash Tables and Binary Search Trees. In the preceding lesson, we introduced the concept of data structures by looking at arrays, linked lists, queues, and stacks. In this lesson, we will use some of these primitive structures to build more complex ones. We'll start the lesson by looking at hash tables, which are useful data structures for fast key value lookup. In the second part of this lesson, we'll learn about a more complex data structure that supports range queries called binary trees. This lesson has 2 topics. Topic A, introducing hash tables, and Topic B, getting started with binary search trees. By the end of this lesson, you'll be able to describe how hash tables work. You'll be able to implement 2 main techniques to deal with hash collisions. You'll be able to characterize different hashing choices. You'll understand and be able to explain the terminology, structure, and operations of binary trees. You'll be able to demonstrate various tree traversal techniques. And lastly, you'll be able to define balanced binary search trees. Now let's begin with Topic A, introducing hash tables. A data structure that gives us the ability to insert, search, and optionally delete elements in a collection is called a data dictionary. Commonly, the type of data used is a key-value pair association, where we insert the key-value pair, but search using a key to obtain the value. Hash tables provide us with a fast data structure for organizing these key-value pairs and implementing our data dictionary. They are useful in a wide variety of applications due to the quick lookup and ease of use for in-memory data storage. Insertion and search operations have a typical average runtime complexity of big O of 1. Let's look at an example problem to help us understand the need for hash tables. Imagine you are a teacher instructing a class of a maximum capacity of 30 students. The students sit at their assigned desks every day. To make your life easier, you decide to assign a sequential number from 1 to 30 to each desk. You then use this number to identify each student and use your self-developed app to bring up the student's records after you enter the desk number. This way, you can quickly look up details such as the student's name, date of birth, notes, and exam history. In this problem, a simple array can be used to store all students' records in memory. Each of the array's positions can contain 1 student record. This would allow you to access the array directly using a strategy of index equals desk number minus 1. If, in a particular year, you have fewer students and not all the desks are occupied, you will place nulls at the corresponding array index. This solution is shown in the figure. This is an example of direct addressing, where each student's record is accessed using a key, the desk number. This type of solution can only be used when the possible key range is small enough to fit in an array which is directly in memory. To help us determine how efficiently we are using memory, we can measure the load factor. The load factor is simply a metric showing how fully utilized our data structure is. When the class is at max capacity, all the elements in the array will contain a record. We say that the load factor of our data structure is 1, or at 100%. If, for example, only 15 students out of 30 spaces have registered for a particular year, this means the load factor is at 0.5 or 50%. A lower load factor value means that we are underutilizing and wasting memory. Now let's expand our example to include not just a class, but an entire school. And instead of teaching just one class, you've now been promoted to the head of the entire school. In this new position, you want to keep student records for every person currently enrolled. You also want to store historical records for any past students that are no longer in the school. So you decide to use the national identification or passport number as a key to uniquely identify each one of your students. Assuming this is a United States or a European school, the national ID or passport number typically consists of 9 numeric digits or more. Since our input range is quite large, directly addressing this would be very impractical. We can still store the students' records in an array size to a few thousand. All we need to do is find a way to squeeze our input key range into our array index range. Essentially, this means mapping our 9-digit numeric passport into a 4-digit one. This job can be done by what is known as a hash function. A hash function would accept a key, like our passport number, and return an array index within the size of our array. We say that a hash function maps our input key universe to our chosen hash range, which in this example is our array size. Using a hash function enables us to use a much smaller array and saves us a lot of memory. However, there's a catch. Since we are forcing a bigger key space into a smaller one, there is a risk that multiple keys map to the same hashed array index. This is what is called a collision. We have a key hash to an already filled position. The strategy on how to deal with collisions together with the choice of the hash function make up our hash table. The following code snippet shows a Java interface that defines our hash table API. We will gradually implement this interface in later sections of this lesson. In Java, the classes java.util.hashTable and java.util.hashMap both implement the interface hash table. The main difference between the two classes is that the hash map is unsynchronized and permits nulls. In this section, we first introduced direct addressing by looking at an example scenario. Later, we expanded the problem to a bigger key space, showing how hash tables can be used in such a scenario. In the next section, we will see 2 common solutions for dealing with hash table collisions. So what do we do when 2 keys hash to the same slot in our array? Overwriting the element in our array is not an option, as this would mean losing records. One common solution to deal with collisions is a technique called chaining. In this solution, the hash table data is stored outside the actual array itself. The idea behind chaining is that each entry in our hash array has a pointer to its own linked list. Any items we add to our hash table are stored in these linked lists. Initially, every entry in the array is initialized to contain an empty linked list. Whenever we insert a particular array slot in the hash table, we insert it at the head of the linked list associated with that position. In this way, we can support hash collisions. Another insert on an already occupied array slot would result in a new item at the head of its linked list. This figure shows an example in which 2 entries with different keys have hashed to the same array slot, resulting in the 2 records stored in the linked list. Searching for a particular key requires first locating the array slot and then traversing the linked list one at a time, looking for the required key until there is a match or the end of the list is reached. The highlighted code you see before you shows the search, get, insert, put, and delete, which is the remove operations. We're making use of Java's linked list collection for this hash table implementation. In the constructor, the array is initialized with the given capacity, and each element is filled with an empty linked list. Using the Java linked list collections enables us to use Java's lambda expressions when searching for the key in the getKey method. When searching, we try to match the key with the ones found in the linked list, and only return the optional value if a match is found. Using the lambda expressions also enables us to implement the delete operation in a clean manner by just calling the removeIf method with a key matching predicate. The hash provider interface in this code simply provides us with a method that implements a hash function. We will implement this interface in the following sections when we explore different hash techniques. The runtime complexity for the chained hash table is dictated by how long our linked lists get. The best case is when every single item we insert in the hash table hashes to a different slot. That is, when there are no collisions. In the best case, we have a runtime of big O of 1, when each linked list only contains one item and we can directly access any item. In the previous section, we saw how we can deal with collisions using linked lists at each array position. A chained hash table will keep on growing without any load limit. Open addressing is just another way of tackling hash collisions. In open addressing, all items are stored in the array itself, making the structure static with a maximum load factor limit of 1. This means that once the array is full, you can't add any more items. The advantage of using open addressing is that since you're not using linked lists, you're saving a bit of memory since you don't have to store any pointer references. You can then use this extra memory to have an even larger array and hold more of your key value pairs. To insert in an open addressed hash table, we hash the key and simply insert the item in the hash slot, the same as a normal hash table. If the slot is already occupied, we search for another empty slot and insert the item in it. The manner in which we search for another empty slot is called the probe sequence. A simple strategy shown in the figure is to search by looking at the next available slot. This is called linear probing, where we start from the array index at the hash value and keep on increasing the index by 1 until we find an empty slot. The same probing technique needs to be used when searching for a key. We start from the hash slot and keep on advancing until we match the key or encounter an empty slot. Linear probing suffers from a problem called clustering. This occurs when a long succession of non-empty slots develop, degrading the search and insert performance. One way to improve this is to use a technique called quadratic probing. This strategy is similar to linear probing, except that we probe for the next empty slot using a quadratic formula of the form h plus ai plus bi squared, where h is the initial hash value and a and b are constants. This figure shows the difference between using linear and quadratic probing with an a equals 0 and a b equals 1. The diagram shows the order in which both techniques explore the array. In quadratic probing, we would change snippet 3.3 to check at array indexes of the following. Linear probing suffers from a problem called clustering. This occurs when a long succession of non-empty slots develop, degrading the search and insert performance. One way to improve this is to use a technique called quadratic probing. This strategy is similar to linear probing, except that we probe for the next empty slot using a quadratic formula of the form h plus ai plus bi squared, where h is the initial hash value and a and b are constants. The figure shows the difference between using linear and quadratic probing with an a equals 0 and a b equals 1. The diagram shows the order in which both techniques explore the array. In quadratic probing, we would change the snippet to check at array indexes of the following. One other probing strategy used in open addressing hash tables is called a double hashing. This makes use of another hash function to determine the step offset from the initial hash value. In double hashing, we probe the array using the expression h plus ih of k, where h is the hash value and h of k is a secondary hash function applied on the key. The probing mechanism is similar to linear probing, where we start with an I of 0 and increase by 1 on every collision. Doing so results in probing the array every h of k step. The advantage of double hashing is that the probing strategy changes on every key insert, reducing the chances of clustering. In double hashing, care must be taken to ensure that the entire array is explored. This can be achieved using various tricks and techniques. For example, we can size our array to an even number and make sure the secondary hash function returns only odd numbers. For hash tables, a hash function maps a specific key's space into a smaller number range. An ideal hash function is one that reduces collisions to a minimum, and when a good hash function is used, each key has the same probability of filling any of the slots in our array. More formally, a hash function, or f, maps keys of a specific data type to integers in a fixed interval, let's say 0 all the way to n-1. We say that f of x hashes the value of x. The hash function can accept only numeric data types. To allow us to use hash tables on more complex data types, we usually need to convert all of these types into numeric representations. This translation varies depending on the type of data. For example, a character can be changed into its UTF-8 or ASCII numeric equivalent. Converting a full string can be done by converting each character separately and then using a strategy to combine the characters into one value. One quick note. In Java, the hash code function or method converts an object into a numeric representation, which is ready to be used by a hash function. It is present in the object class and can be overridden using a custom implementation. There are many techniques in how we can map keys from a wide range into smaller ones. An ideal hash function, again, is one that reduces collisions to a minimum. In other words, when a good hash function is used, each key has the same probability of filling any of the slots in our array. In practice, finding an ideal hash function is very difficult unless we know the input distribution. A simple technique to implement a hash function is what is known as the remainder method. The hash function simply takes in any numeric key, divides it by the table size or the size of the array, and uses the resultant remainder as the hash value. This value can then be used as the index of the array. The following code shows how the remainder hashing method can be implemented in Java using the modulus operator. The remainder method might result in many collisions if care is not taken when choosing an appropriate table size. Once again, consider the example given at the beginning of this section, where we are using the student's passport or national ID number to identify a student in the school. To demonstrate the problem, we use an array-based hash table with a size of 1,000 elements. It just so happens that in the country where the school is based, the last 4 digits of the passport numbers represent the year of birth of the passport holder. A better choice of a table size is to use a prime number, ideally not too close to the power of 2. For example, the value of 1,447 is a good choice in our example, since it's not too close to 1,024 or 2,048, 210 and 211 respectively, and it's also a prime number. Using this value as a table size for our example would reduce the number of collisions. Using the remainder method restricts us on the choice of size for our hash table in order to reduce the chance of collisions. To address this, we can use a different hashing technique called the multiplication method. In this method, we multiply the key by a constant double value, k, in the range of greater than 0 and less than 1. We then extract the fractional part from the results and multiply it by the size of our hash table. The hash value is then the floor of this result, where k is a decimal in the range between 0 and 1, s is the size of the hash table, and x is the key. In the multiplication method, we multiply the key by a constant double value k in the range of 0 less than k less than 1. We then extract the fractional part from the result and multiply it by the size of our hash table. The hash value is then the floor of this result. In the highlighted code before you, you see an implementation of this. We're implementing a class with a method that accepts an integer and returns a hash value using the multiplication method. The constant k is passed in as the class constructor. So that's why we have an integer hash key taking 2 arguments, the key and the table size. Both the remainder and multiplication hashing methods have a common vulnerability. If an attacker knows the details of a hash function, like the size and the constant values, they could devise an input key sequence resulting in a collision on every item, turning our hash table into a linked list, and slowing down our program. To address this problem, a hashing technique called universal hashing can be used. This works by choosing a random function from a universal set of hash functions at the start of execution. It makes it difficult for an attacker to guess the exact workings of the hashing technique used. And while using this technique, the same sequence of keys will produce a different sequence of hash values on every execution. The following code snippet that you see before you is a Java implementation of universal hashing suitable for integer-type keys. Notice how our implementation makes use of the big integer class to work out the hash key. This is needed because multiplying a long Java numeric type with a large integer might result in a big enough value that exceeds the maximum capacity of a Java long. The choice of p in this method is such that any integer key input will always have a smaller value since in Java an integer has a maximum value of 2 to the 31st power. Java provides hash tables and built-in hashing mechanisms using the object hashcode method. As a result of this, it's very difficult to implement a universal hashing table which integrates with Java's existing hashcode method, since the I and j variables in the code would have to be shared between different objects being inserted in the same table. Universal hashing provides us with good results, minimizing collisions, and is immune to malicious attacks since the function parameters are chosen at random. Now let's get started with topic B, getting started with binary search trees. Like hash tables, binary search trees are fast lookup data structures for organizing key value pairs and implementing the data dictionary operations. In addition to providing insert, search, and delete, binary tree supports efficient querying, such as finding minimum and maximum, successor, and predecessor. When using balanced binary search trees, insert and search operations have a worst-case runtime complexity of big O of log n. This is a big theoretical improvement over the worst-case scenario of a hash table, which is big O of n. The structure of a binary tree is composed of a series of nodes connected together via pointers. This figure shows the fundamental relation between nodes. Each node can have a maximum of 2 child nodes, a left one and a right one. Each node, except the top level node, also has exactly one parent. This figure shows some more terminology applied to the binary trees. In this diagram, we also show that binary tree nodes can hold data items by showing the nodes storing different shapes. The top level node is called the root node. The root node in a tree structure is the only node that doesn't have a parent. Nodes that don't have any children are called leaf nodes. The height of a tree is the number of hops it would take you to get from the root node to the furthest leaf node. The diagram shows an example of a tree which has a height of 2. The height of a tree is an important metric as it affects the performance. The shallower a tree is, or smaller height, the more performant a tree structure is. Similar to a linked list, the binary tree structure is modeled using pointers and node objects. In a linked list node, we only have a next pointer referencing the next node in the list. Similarly, in a binary tree node, we have 2 pointers, each one linking to one child. These are the left and right child pointers. The following code snippet shows how you can model a binary tree node using a Java class. We can then have another class representing the binary tree itself, where the operations will be implemented. This class needs to only hold a pointer to the root node, since any node can be reached by starting from the root node and navigating down. This is where we have the binary tree interface. Binary search trees are normal binary trees in which data is organized in an ordered manner. Consider the same problem we encountered in the previous topic, of the school keeping students' records by using the passport numbers as a key. The figure shows an example of how you can organize the data in a binary tree. Note how at each node the left child has a key which is less than its own. On the other hand, the right child has a larger key. Shown in the diagram, the root node has a left child containing a key of a smaller value than the root key. On the other hand, the right child has a key of a larger value than the root. This rule is repeated throughout the entire tree. In a binary search tree, the left child will always have a smaller key than the parent, while the right child will have a larger one. Using this binary search tree property, we can create efficient operations on the tree structure. As a result of this simple rule, the tree exhibits important properties. For example, note how all the nodes that are descendants of the left child of the root node have a smaller key than the root. This property is valid for any node of the tree. All keys on the left subtree of a node will always have smaller keys, and vice versa. Searching in a binary tree requires us to follow some simple instructions. We start at the root, and at each node we ask ourselves, is the key we're looking for equal to, less than, or greater than the key on this node? If the key is equal, we're done and we have found our node. If the key is less, we follow the left child pointer, otherwise we follow the right one. We repeat this step until we find our key or hit a null child pointer. The highlighted code snippet shows the search implementation. In this implementation, we use the power of recursion to perform the search. We start by checking if the tree is empty by checking if the root is null. If a root node is present, we compare the key and either return the value or recursively search the child nodes. To compare the key, we assume the provided key implements the comparable interface. Using Java's optional flat mapping makes our implementation more concise. Also, notice line 41. In that, Java's object A.compareToObjectB method in the comparable interface will return a negative integer, 0, or a positive integer, as object A is less than, equal to, or greater than object B. Therefore, the following statement on line 41, comparable key.compareTo node.getKey less than 0, is conceptually the same as key less than node.getKey. Inserting in a binary tree follows the same logic as the search operation. We start from the root and keep on looking for a location where we need to create a new node. This is shown in the following code snippet. Like the search operation, this Java implementation is also recursive. If the root node is absent, we just create a new one. Otherwise, we recursively insert the key value pair each time by choosing the left or right child depending on the value of the key. We have 3 stopping conditions for the recursive call that are as follows. When the key is equal to the 1 on the node, we simply overwrite the entry. When the left child is not present, we create a new node with the key value pair. And lastly, when the right child is not present, we create a new node with the key value pair. Inserting in a binary tree follows the same logic as the search operation. We start from the root and keep on looking for a location where we need to create a new node. This is shown in the highlighted code. Like the search operation, this Java implementation is also recursive. If the root node is absent, we just create a new one. Otherwise, we recursively insert the key value pair each time by choosing the left or right child, depending on the value of the key. We have 3 stopping conditions for the recursive call that are: first, when the key is equal to the 1 on the node, we simply overwrite the entry. Second, when the left child is not present, we create a new node with the key value pair. And our third stopping condition is that when the right child is not present, we create a new node with the key value pair. The highlighted code illustrates this. Now, binary tree deletion requires matching the subtree structure with a number of patterns and performing different actions with each case. In some situation, it requires you to connect the subtree with the parent of the deleted node, which can be quite complicated. For this reason, the deletion algorithm is not included here. We can search for a minimum key in a binary tree by implementing the following highlighted methods. The method needs to find the minimum key in the tree and return it. If the tree is empty, it should return an empty optional. Finding the minimum in a binary search tree requires us to always follow the left child node until we reach a node with no left child pointer. The highlighted code demonstrates this. Traversing a binary tree is the process of stepping through each node of the tree and performing some sort of action on the data contained in the node, such as printing the key value pair. There are 2 main techniques to perform tree traversal: the depth-first search and the breadth-first search, more commonly known as DFS and BFS respectively. In the depth-first search, the algorithm goes down a path of tree nodes until it cannot go any further. Once it cannot go further, it backtracks and discovers any remaining unexplored branches. A recursive implementation is shown in the following code. In this traversal method, a different output sequence is produced depending on where the action is executed in the method. In pre-order execution, we perform the action immediately, as soon as a new node is discovered. A post-order execution, on the other hand, is when both children of a node have been explored and we are about to backtrack. An in-order execution is done when the left child has been processed, but before processing the right one. When using an in-order traversal, the keys in the binary search trees will be processed in ascending order. Here we have an example of that ascending order. In the breadth-first search traversal, the algorithm explores the binary tree one level at a time, left to right. The traversal starts from the root node and finishes at the leaf nodes. The output of an example binary tree is shown in the figure. To implement a BFS traversal of a binary tree, we can make use of a queue initialized to contain the root node. Then, while the queue is not empty, we read the first node on the queue, process it, and add first the left and then the right child to the queue. We show the pseudocode of this as follows. Breadth first search root. If the root is not equal to null, the queue will be equal to the create queue method. We can then enqueue the queue at the root node. And as long as it's not empty, we can dequeue the queue. Finally, we process the node. If the node on the left is not equal to null, we can enqueue that node. And similarly, if the node on the right is not equal to null, we can enqueue the right node. The performance of a binary search tree is proportional to its height. This is because the search and insert operations start from the root and proceed down the tree, one node at a time, doing a key comparison at each step. The taller the tree, the more steps are needed to accomplish this. Thus, if we determine the maximum possible height of a binary tree in relation to its input, we can find the worst runtime complexity. If we insert keys in a binary tree, by always adding on the right child of the parent node, we end up with a tree similar to the one shown on the left-hand side of the figure. In this diagram, only the right child pointers on each node are being used. We end up with a tree of height n, where n is the number of items added to our data structure. We get this kind of one-sided tree when the key input pattern is in order. In the example shown in the figure, we first insert 5 as a root, then 7 is added as the right child, the next is 12 as the next right child, and so on. Always inserting an increasing number returns in the next node on the right. This one type of input pattern makes our binary search tree operations, search, insert, and delete, behave in the worst case runtime of big O of n. In the figure on the right-hand side, we show another binary tree containing the same keys. This binary tree has been restructured with the effect that the tree is now shorter. Note that the tree is still valid. That is, the left child always has a key that is smaller than its parent, and vice versa. A balanced binary tree has a height of about log 2n. If we manage to find a way to rebalance the binary search tree at each insert in big O of log n, or better, the worst case runtime performance for inserts and searches would also be of big O of log n. Luckily, various algorithms exist that self-balance the tree structure as you perform inserts. Some of the most common ones are as follows: AVL trees, red-black trees, and AA trees. All of these algorithms check that the binary tree is following specific balancing rules at key insert. If, due to a new node being inserted, the tree becomes unbalanced, the self-balancing algorithm kicks in and restructures some of the nodes to keep the tree balanced. The technique to rebalance the nodes relies on tree rotations, where under certain conditions, some of the parent and child nodes are rotated. More importantly, these modifications are also performed in the worst case of big O of log n, meaning that both inserts and searches on binary trees have a worse runtime complexity of big O of log n. In this section, we will examine tree rotations as they are the base operation for most self-balancing trees. The figure shows an example of a left and right rotation. Note how the node being rotated, node 5 in the right rotation and 9 in the left rotation, ends up being the new parent. More importantly, there is a constant number of child pointer reassignments. The properties of a binary search tree are still valid after a tree rotates. That is, a left child pointer always has a smaller key that points to its parent and vice versa. This means that we can perform any number of these tree rotations and our binary search tree will still be valid. The below code shows how we perform a right rotation in Java. The method accepts a top-level node that needs rotation and its parent node. The method requires the parent node since it has to reassign its child pointer. Performing the opposite right rotation on the tree node is the mirror image of the following method. The highlighted code shows how we perform a right rotation in Java. The method accepts a top-level node that needs rotation, and its parent node. The method requires the parent node since it has to reassign its child pointer. Performing the opposite right rotation on the tree node is the mirror image of the left rotation that you see above the current method. In this lesson, we have studied two of the most commonly used data structures for implementing the data dictionary operation. Hash tables provide fast in-memory insertion and lookup operations. In addition, binary trees also give us the ability to perform various range queries, such as successor, predecessor, minimum, and maximum. In this lesson, we have seen examples of both data structures and implementations of these operations. Now it's time for Lesson 4, Algorithm Design Paradigms. In the last lesson, we learned about hash tables and binary search trees. Today, we will start with the algorithm design paradigms. These design patterns can be seen as the generic methods or approaches that motivate the design of a class of algorithms. Just as an algorithm is a higher abstraction than a computer program, an algorithm design paradigm is an abstraction higher than an algorithm. The choice of an algorithm paradigm is an important one when designing an algorithm. This lesson will focus on the following 3 algorithm paradigms: greedy, divide and conquer, and dynamic programming. By becoming familiar with these higher abstractions, you can make more informed decisions when designing algorithms. There are obviously more algorithm design paradigms, but these 3 already cover a broad range of problems. Some other paradigms we're not talking about in this course are backtracking and prune and search. There are even paradigms focused on specific branches of computer science. The sweep line algorithms in computational geometry is an example of this. This lesson has 3 topics. Topic A, introducing greedy algorithms. Topic B, getting started with divide and conquer algorithms. And Topic C, understanding dynamic programming. By the end of this lesson, you will be able to describe greedy, divide and conquer, and dynamic programming algorithm paradigms. You should be able to analyze common problems solved by using the described paradigms. You should be able to list the properties of a problem to be solved by each paradigm. And lastly, you should be able to solve some well-known problems that explain the applicability of each paradigm. Let's get started with Topic A, introducing greedy algorithms. Algorithms typically go through a sequence of steps, where in each step you have a set of choices. Greedy algorithms, as the name might suggest, follow the heuristic of making the locally optimum choice at each step, with the hope of arriving at a global optimum. To better understand what we mean by this, let's introduce a problem. Peter is an energetic guy and usually has many things to do in a given day. However, with the amount of things he wants to do, he is usually unable to do them all in a single day. What he usually does after waking up is write up a list of activities that he has to do, along with their time span. Then, looking at that list, he devises a plan for the day, trying to accommodate as many activities as possible. Now, being an energetic guy, he usually rushes through this process and finds himself doing fewer activities than possible throughout the day. Can you help him maximize the amount of activities he can do in a day, given his schedule? An example of a schedule for Peter is given in the following table. This is known as the activity selection problem. The problem is to schedule several competing activities that require exclusive use of a common resource, which is Peter in this case, with the goal of selecting a maximum size set of activities that are mutually compatible. In other words, we are trying to find the biggest set of activities that Peter can perform in a given day. Each activity, AI, has a start time of SI and a finish time of FI. 2 activities, AI and AJ, are considered compatible if the intervals SI to FI and SJ to FJ do not overlap. For example, if SI is greater than or equal to FJ, or SJ is greater than or equal to FI. Looking at Peter's schedule and converting the start and finish time to minutes since the start of a day, we can arrive at the following table. To convert the times to minutes since the start of the day, we multiply the hours by 60 and add the minutes. For example, activity 1 runs from 10 to 12 o'clock, and 10 o'clock is 600, or 10 times 60 plus 0 minutes since the start of the day. And 12 o'clock is 720, 12 times 60 plus 0 minutes since the start of the day. For this example, the subset A1, A3, A5, and A6 consists of mutually compatible activities as their times do not overlap. It is not a maximum subset, that is, we can find a set with a larger number of activities, since the subset A3, A4, A5, A6, A7, and A11 is larger. Note that the order of the activities is A4, A7, A11, A3, A5, and A6. In fact, it is a larger subset of mutually compatible activities. It is not the only one. Another possible larger subset would be A1, A7, A11, A3, A5, and A6. So how should we approach this problem to find the maximum set size of activities that are mutually compatible? It turns out that we should do the greedy choice. What this means is that at each step of the algorithm, from the set of activities that we can still perform, we should choose one greedily. The greedy choice may not be immediate, but you can intuitively think that we should select activities that leave Peter available for as many other activities as possible. Hence, from the set of activities that we are able to choose, we must choose the first one to finish, as that is the activity that would leave Peter available for as many of the activities that follow as is possible. If we sort activities by finish time, We can then always select the first activity we find that is compatible with the last activity selected for Peter. We can implement the greedy algorithm in Java to solve this activity selection problem. A possible implementation is shown in the highlighted code. Here we have the sorted activities. There are two basic ingredients every greedy algorithm has in common. They are as follows. First, the optimal substructure property. An optimal solution to the problem contains within itself optimal solutions to its subproblems. And second, the greedy choice property. From a local optimum, we can reach a global optimum without having to reconsider decisions already made. To gain more insight about greedy algorithms, let's look at another problem that is solvable by a greedy algorithm. Huffman codes represent a way of compressing data effectively. Data is considered to be a sequence of characters. Huffman's greedy algorithm uses a table with the frequency of each character to build up an optimal way of representing each character as a binary string. To illustrate this, imagine we have a 100,000 character data file that we wish to store in a compressed fashion. The frequency of each character in the data file is given by the following table. There are various ways to represent this information. For the purpose of this problem, let's say that we want to design a binary character code in which each character is represented by a unique binary string. We can call this a code word. One option is to use a fixed length code. For example, each character is represented by a code word of the same size. If we opt for that, we need 3 bits to represent each of the 6 characters, as shown in the table. Using this method, we need 300,000 bits to code the entire sequence of characters. Can we do better? A variable length code can do a lot better than a fixed length code. Since we want to minimize the size of the compressed sequence of bits, we want to give short code words to frequent characters and long code words to infrequent characters. A possible code for this character sequence is shown in the following table. Instead of 300,000 bits, this code requires only 224,000 bits to represent the character sequence. Using this code, we save around 28% of space. The code we have presented is also an optimal character code for the sequence, as we shall see. Before we start studying an algorithm to solve this problem, we should introduce something called prefix codes. Prefix codes are codes in which no code word is also a prefix of some other code word. As you may have seen from the proposed variable length code, we must make sure that no code word is also a prefix of some other code word, since we want to concatenate on code words and unambiguously be able to decode it afterwards. For example, using the code shown previously, we can encode the string ABC as 0101100. Since no code word is a prefix of any other, decoding is vastly simplified, as we can identify the initial code word, translate it, and repeat the process on the remainder of the encoded sequence. A convenient, or at least for decoding purposes, representation of prefix codes is a binary tree whose leaves are the characters of the original data sequence. For the proposed variable length code, we have the following binary tree. The binary code word for a character is the path from the root to that character, following in the binary digits of each edge. Note that each node also holds the frequency of characters under its subtree. Such a tree also has some interesting properties. A tree for an optimal prefix code has exactly C leaves, C being the alphabet from which the characters are drawn. The number of internal nodes is exactly C minus 1. We also know that the number of bits necessary to encode a particular character in a sequence is equal to the frequency of that character multiplied by the depth of the leaf that holds the character. As such, the number of bits required to encode the full character sequence is simply the sum of these values for all the characters in the alphabet. If we can build such a tree, we can compute an optimal prefix code. David A. Huffman invented a greedy algorithm to construct an optimal prefix code called a Huffman code. Its basic idea is to build the tree in a bottom-up fashion. We start with just the leaf, one for each character. We then repeatedly join the 2 least frequent nodes until we are left with a single node, which is the root of the tree. In this first topic, we introduced the greedy paradigm of algorithm design, using the activity selection problem as a running example. We introduced the 2 properties a problem must observe to be optimally solved by a greedy algorithm: optimal substructure and greedy choice. To gain intuition about the applicability of greedy algorithms, we later explored 2 other problems that are solvable by a greedy approach: Huffman coding and Egyptian fractions. If we need to implement an algorithm capable of building the tree that generates the binary code words for the character in a data file using Java, we can look at the highlighted code in front of you. Here, we use a priority queue to store nodes with the character frequency. We also repeatedly join the two nodes with the least frequencies until we're left with a single node. Now it's on to topic B, getting started with divide and conquer algorithms. In lesson 2, we introduced, among other sorting algorithms, merge and quicksort. A peculiarity of both algorithms is that they divide the problem into subproblems that are smaller instances of the same, solve each one of the subproblems recursively, and then combine the solutions to the subproblems into the solution for the original problem. This strategy forms the basis of the divide and conquer paradigm. In a divide and conquer approach, we solve a problem recursively, applying the following 3 steps at each level of recursion. Divide the problem into more than one subproblems that are smaller instances of the same problem. Then, conquer the subproblems by solving them recursively. Eventually, the subproblem sizes are small enough for them to be solved in a straightforward manner. Lastly, combine the solutions to the subproblems in the solution for the original problem. When a subproblem is large enough to be solved recursively, we call that the recursive case. When a subproblem becomes small enough that the recursion is no longer necessary, we say that we have reached to the base case. It is common to solve subproblems that are different from the original problem, in addition to the subproblems that are smaller instances of the main problem. Solving these problems is considered to be part of the combined step. In Lesson 2, Sorting Algorithms and Fundamental Data Structures, we saw that the runtime complexity of merge sort was big O of n log n. We can also see that the worst-case running time, T of n, of merge sort can be described by the following recurrence. These kinds of recurrences arise frequently and characterize divide and conquer algorithms. If we generalize the recursion to the following, where a is greater than or equal to 1, and b is greater than 1, and f of n is a given function, we have the recurrence for the worst-case running time of a divide and conquer algorithm that creates subproblems, each being of size 1 divided by b of the original problem, and in which the combined steps together take f of n time. When it comes to divide and conquer algorithms, it is often easier to come up with this recursion, but harder to derive the runtime complexity. Fortunately, there are at least 3 methods to provide big O bounds for these recurrences: the substitution method, the recursion tree method, and the master method. For the purpose of this course, we will only be focused on the master method. The master method provides a way to solve recurrences of the following form: T of n equals a times t of n divided by b, plus f of n, where a greater than or equal to 1 and b greater than 1 are constants, and f of n is an asymptotically positive function. The master method consists of 3 cases, which allow you to solve these kinds of recurrences quite easily. It's important to note that the recurrence is not actually well defined, since n divided by b may not be an integer. Whether we replace it with the floor or ceiling of the n divided by b division, it will not affect the asymptotic behavior of the recurrence. Now that we know what characterizes a divide and conquer algorithm and are familiar with the master method to derive bounds from recurrences, let's look at a problem solvable by a divide and conquer approach. The problem we will be looking at is the problem of finding the closest pair of points on a plane. We are given an array of n points in the plane, and we want to find out the closest pair of points in this array. Recall that the distance between 2 points P and Q is given by the following. The distance between them will equal the square root of px minus qx squared, where x is the x-coordinate, plus py minus qy squared, where y is the y-coordinate. Our first approach may be to compute the distance between each pair and return the smallest for a runtime complexity of big O of n squared. The following snippet implements this algorithm. And here you see our point pair candidate equaling a new point pair object and the points of each one being gathered as a smaller and larger array. If the candidate distance is less than the best candidate distance, then the best would be equal to the new candidate. The proposed algorithm solves this problem, but we can do better by using a divide and conquer approach. The algorithm makes use of a pre-processing step in which it sorts the input array by its x-coordinate. Then it proceeds as follows. First, it divides the array into 2 halves. Then it recursively finds the smallest distance in both subarrays which is the conquer portion of this. Lastly, it combines the results by taking the minimum distance from both halves and additionally considers pairs so that one point in the pair is from the left subarray and another is from the right subarray. The approach seems straightforward except for the combine part. After finding the minimum distance d from both the left and right subarrays, we have an upper bound of the minimum distance for this subproblem. Therefore, we only need to consider points whose x-coordinate is closer than d to the middle vertical line. We can then sort those points by y-coordinates and find the smallest distance in the strip as shown in this diagram. The highlighted code snippet computes the minimum distance in the strip considering the minimum distance computed so far. Looking at this code, it seems to have a runtime of big O of n squared, which doesn't really improve our brute force approach. However, it can be proved geometrically that for every point in the strip, a maximum of 7 points after it need to be checked. This reduces the runtime of this step to big O of n log n due to the sorting step. We can do even better on this step if we sort the initial input by the y-coordinate and keep a relationship between the points on the x-sorted array and the y-sorted array, effectively reducing the runtime of this step to big O of n. After having computed the minimum distance from both subarrays in the middle strip, we have found the closest pair of points in the subarray. Now let's proceed to topic C, understanding dynamic programming. After greedy and divide and conquer, we'll turn our attention to dynamic programming. Dynamic programming is an algorithm design paradigm that also attempts to solve optimization problems by combining solutions with subproblems. Unlike divide and conquer, subproblems need to exhibit optimal substructure for dynamic programming to be applicable. There are two key ingredients that an optimization problem must have for dynamic programming to be applicable: optimal substructure and overlapping subproblems. First, the optimal substructure. Optimal substructure is something we already covered when we introduced greedy algorithms. Recall that a problem exhibits optimal substructure if an optimal solution to the problem contains within it the optimal solutions to those subproblems. There's a common pattern when trying to discover optimal substructure for a problem that can be explained as follows. Now let's discuss overlapping subproblems. Another ingredient that optimization problems must have for dynamic programming to apply is that the space of subproblems should be small. Hence, a recursive algorithm for the problem should solve the same subproblems repeatedly. Typically, the total number of distinct subproblems is a polynomial in the input size. A recursive algorithm is said to have overlapping subproblems if it visits the same problem repeatedly. It's therefore typical for dynamic programming algorithms to cache solutions to subproblems to avoid recomputation of the same solutions over and over. To showcase a dynamic programming solution, exploring the properties of the problem that make it solvable by this technique, we shall look at the 0 to 1 knapsack problem. Let's say you're given weights and values of n items. You must put these items in a knapsack of capacity W to get the maximum value of the knapsack. You cannot break an item, you can either pick it or not pick it, hence the 0 to 1 property. In other words, you are given two arrays with values of ranges from 0 to n-1 and weights with a range of 0 to n-1 as well, which represent values and weights associated with the n items respectively. You want to find the maximum value subset of values array such that the sum of weights of the subset is smaller than or equal to W. The first immediate solution to this problem is to consider all subsets of items and calculate the total weight and value of all subsets, considering only those whose total weight is smaller than W. To consider all subsets of items, we can observe that there are two choices for each item. Either it is included in the optimal subset, or it is not. Hence, the maximum value we can obtain from n items is the maximum of two values. Either 1, the maximum value obtained by n-1 items, and W weight, that is, they don't include the nth item in the optimal solution, or 2, the value of the nth item plus the maximum value obtained by n-1 items, and W minus the weight of the nth item. for example, including the nth item. We can solve the 0 to 1 knapsack problem using a recursive approach. Remember, this is a recursive top-down approach, so it repeatedly computes the same subproblems for an exponential runtime complexity of 2 to the nth power. The highlighted code snippet solves this problem and shows this recursive approach. In the method recursive aux, if n is equal to 0 or w is equal to 0, we'll simply return a 0. But if the weights of n minus 1 are greater than w, we'll return and call the same function recursively, passing the new value of n minus 1. The longest common subsequence is solvable with a dynamic programming algorithm. In this case, we're trying to find similarities between two given sequences by computing the longest common subsequence, LCS, between them. A common subsequence of two given sentences is a sequence whose elements appear in both the first and the second in the same order, but not necessarily consecutively. The problem is usually applicable when finding DNA similarities of different organisms. In the highlighted code snippet, we see the solution for this. Using the recurrence of a bottom-up fashion, we can produce the dynamic programming algorithm to compute the length of the longest common subsequence of two strings. Here we pass two strings into the length method. We have an integer mn of each length, and we create a c variable that's an instance of the new m plus 1 and n plus 1. Then we have nested for loops, and inside the inner loop, if the character at I minus 1 is equal to the character at j minus 1, then Cij, which is that array, would be equal to Ci minus 1, j minus 1, plus 1. Otherwise, Cij would equal the maximum of Ci minus 1j and Cij minus 1. Then we would simply return C and the integers m and n. In this lesson, we have discussed three different algorithm design paradigms. We've seen example problems for all of them and discussed how we can identify whether problems may be solvable by one of the given paradigms. In the next lesson, we will be focusing on some string matching algorithms that use the paradigms introduced here. Now for Lesson 5, String Matching Algorithms. String matching algorithms are quite common in text editing programs. These kind of programs frequently need to find all occurrences of a pattern in the text, where the text is usually the document being edited, and the pattern is a word supplied by the user. Since text editing programs aim to be responsive, having efficient algorithms to solve the string matching problem is fundamental. This lesson has three topics. Topic A will cover naive search algorithms. In Topic B, we'll cover getting started with the Boyer-Moore string searching algorithm. And lastly, Topic C, where we cover introducing other string matching algorithms. By the end of this lesson, you should be able to list common string matching algorithms. You should be able to solve the string matching problem. You should be able to devise a naive algorithm to solve the string matching problem. And lastly, you should be able to implement the Boyer-Moore string search algorithm to carry out string search in literature. Now let's dive into Topic A, a naive search algorithm. A data structure that gives us the ability to insert, search, and optionally delete elements in a collection is called a data dictionary. Commonly, the type of data used is a key-value pair association, where we insert the key-value pair, but search using a key to obtain the value. Now, hash tables will provide us with a fast data structure for organizing these key-value pairs and implementing our data dictionary. They are useful in a wide variety of applications due to the quick lookup and ease of use for in-memory data storage. Insertion and search operations have a typical average runtime complexity of big O of 1. The string matching problem has two inputs. First, an array T of range 1 to n of length n, and an array P of range 1 to m of length m, where it's less than or equal to n. The elements of T and P are characters from the same finite alphabet, usually called sigma. For instance, we may be searching in binary strings, in which case our alphabet is 0, 1. Or we may be searching in strings of lowercase letters, in which case our alphabet is a range of small letters from A to Z. The character arrays P and T are usually called strings of characters. We're interested in finding occurrences of pattern P in text T. We say that pattern P occurs in text T if we can align the pattern P with text T so that all characters in P match the ones in T. When aligning, we need to shift pattern P 0 or more times to the right. Therefore, in the string matching problem, we're interested in valid shifts with which pattern P occurs in text T. We say that pattern P occurs with a shift S in text T if the pattern P occurs beginning at position S plus 1 in text T. In other words, we need to shift P from the start of text T S times to the right in order to find a match. In its essence, the string matching problem aims to find all valid shifts with which pattern P occurs in a given text T. Two common examples besides text editing programs are finding patterns in DNA sequences and finding web pages that are relevant to queries in internet search engines. Now that we've formalized the string matching problem, let's look at the naive algorithm to solve it. As we described the string matching problem, we said that we were interested in finding all valid shifts with which pattern P occurs in a given text T. If we translate that notion directly into an algorithm, we're able to arrive at the naive string matching algorithm. In order to build the naive string matching algorithm, we'll need to return all valid starting positions or shifts in the text T in which the pattern P occurs. The highlighted code shows this. Here we're implementing the match method of the naive string matching class. We repeatedly shift pattern P along text T, matching all the characters in it with the characters aligned in T. When a match occurs, we keep track of the index in T, where it did. The naive search algorithm takes big O of n-1 plus 1 times m time, which is a tight bound on the worst case. We can imagine a worst case of the naive search algorithm if we have a text string with the character A repeating for n times. That is such as a to the 5th power equals string AAAA, and the pattern AM for m is less than or equal to n. In this case, we have to execute the inner loop m times to validate that shift. The naive search algorithm can be improved if we know that all characters in pattern P are different. In this case, whenever we fail validating a shift because P times J doesn't match T of I plus J, we don't need to backtrack. Instead, we can start validating the next shift on I plus J, therefore reducing the running time of the algorithm to big O of n. Now we can move on to topic B, getting started with the Boyer-Moore string searching algorithm. The Boyer-Moore string searching algorithm was introduced by Robert S. Boyer and J. Strother Moore in 1977 and builds upon the naive search algorithm by intelligently skipping certain sections of the text. One key feature of the algorithm is that it matches the pattern from right to left instead of left to right, using to its advantage a couple of shift rules that improve its running time. To understand the effect of these rules, let's build the Boyer-Moore algorithm from our naive search algorithm. We'll start by modifying the matching on the pattern so that it operates from right to left. The following code demonstrates this. Using the naive string matching algorithm as the base, let's look at some rules that allow us to intelligently skip certain shifts. The idea of a bad character rule is to identify mismatches between a character in the pattern and a character in the text so that we can safely skip certain shifts. In the example provided in the table, we successfully matched the suffix A and H, but then arrived at a bad character since B does not equal H. Whenever this happens, we're sure that it will only be possible to find a valid shift starting from the next shift that solves this mismatch. This means that we can shift P until either of the following conditions are true. The mismatch is turned into a match, or the pattern moves past the mismatched character. We can turn a mismatch into a match whenever the pattern has characters to the left of the mismatched character that match the character in the text. Otherwise, we must move the pattern past the mismatched character. In the example provided in the table, we have another B at P1. So we can shift P until P1 aligns with T3 as follows. We've safely skipped the check for one shift. Now we have a mismatch right in the first character. Let's try to apply the bad character rule. First, let's see if we can turn the mismatch into a match. Unfortunately, that is not possible because the character C is absent from P. In this case, we shift the pattern past the mismatched character as follows. We've successfully skipped checking 5 shifts and arrived at a valid shift. The bad character rule will help us optimize the naive string matching algorithm, but only if we can efficiently find the correct number of times to shift. Let's assume we have access to a two-dimensional array of a range of 1 to m and 1 to e being the size of our alphabet. For convenience, let's call this array left and assume that left ij gives us the closest index k of character j in p, so that k less than I, or is -1 if character j isn't found to the left of I and p. If we're able to build such an array, we can improve our naive string search algorithm by considering possibly larger skips, given by the information in left. The following code snippet shows us how we can use the left array to improve our naive string searching algorithm as follows. The highlighted code shows you an implementation of the bad character rule. Recall we have to pre-process string p to build the left array that allows us to use the bad character rule efficiently. In the highlighted code, we are looping around the length of m, which is the p length of string. Now inside there, we have a for loop where we can assign left ij to be equal to -1, one of the returns. Then we can loop around the same I under m, and if I is not equal to 0, there's a match. We can then loop around j as long as j is less than e, which is 256 characters, and assign left ij to be equal to left I -1 and j. Then we can have left I and p character at I equal to I. The good suffix rule presents a complementary method to enhance our search for valid shifts. To identify when the good suffix rule is applicable, let's look at the example given in the following table. When found in a situation where we have matched a suffix of p, but have found a mismatch, using the good suffix rule and considering t as the matched suffix, we can try to find the next shift that solves the mismatch by carrying out either of the following cases. First, find another occurrence of t to the left in p. Second, find a prefix of p which matches a suffix of t. And third, move p past t. Considering case 1, we can try to shift p by 3 to align other occurrences of t in p, starting at p4. As we can see, the letter to the left of that occurrence of t in p3 is c, which is exactly the same as the one that provoked the mismatch. Therefore, we should always try to find a t that is followed on the left by a character that is different from the one that provoked the mismatch. A variant of the good suffix rule, which ignores the character on the left of t, is called the weak good suffix rule. If we can't find another occurrence of t in p, the best we can do with this rule is to find a prefix of p that matches a suffix of t, entering case 2. This table illustrates this case. In this case, we found a mismatch at p1, but we can't find another occurrence of BAB to the left of it. We can, however, find a prefix of AB that matches a suffix of TAB and shift P so that these align. Whenever we can neither find another occurrence nor a prefix of T, we're left with moving P past T in T. The implementation of the good suffix rule also requires some pre-processing on P. To understand the pre-processing that is necessary, we need to introduce a concept of a border and a proper prefix and suffix. A prefix of string S is a substring of S that occurs at the beginning of S. A proper prefix of string S is a prefix of S that is different than S. Consider that S is always a prefix of S. A suffix of string S is a substring of S that occurs at the end of S. A proper suffix of string S is a suffix of S that is different from S. Consider that S is always a suffix of S. A border is a substring of a given string that is both a proper prefix and a proper suffix. For example, given the string CCACC, there will be two borders, C and CC. CCA is not a border. The processing step for the good suffix rule is divided into two steps, one for case 1 of the rule and another for case 2. In case 1, the matching suffix is a border of a suffix in a pattern. For example, if P equals AACC ACC AC, and we have T equals AC, a suffix of P, then we need to find a suffix of P that has AC as a prefix, constituting a border of the suffix. The string ACC AC is a suffix of P and has AC as a border. Therefore, we need to find the borders of the suffixes of the pattern. But even after finding them, we need to be able to map a given border to the shortest suffix that has this border so that we're able to shift accordingly. Moreover, to follow the strong good suffix rule, the border could not be extended to the left by the same symbol that caused the mismatch. The following code snippet shows how we can use the left array to improve our naive string searching algorithm as follows. The Boyer-Moore algorithm is typically used with one or both the bad character and good suffix rule. When used with both rules, the shift that is to occur is the biggest one produced by the rules. The Boyer-Moore algorithm improves the naive search algorithm in average case, but is still big O of n times m. In the worst case, that case being the same described in the previous topic, that is, a repeated group of characters both in the pattern and in the text. The highlighted code shows a Java implementation of the Boyer-Moore algorithm. We needed to integrate the bad character rule with the good suffix rule to produce the complete algorithm. The idea here is to use the rule that gives us the bigger or best shift in each situation. So, we implemented the match method of the Boyer class and combined the snippets and changed the skip logic to choose the best of both rules. The highlighted snippet shows this in action. Now let's begin topic C, introducing other string matching algorithms. Even though the Boyer-Moore string search algorithm is the standard benchmark for practical string searching in literature, there are other string matching algorithms that are also suitable for different purposes. In this small topic, we'll present the following three, which are the most famous ones: the Rabin-Karp, the Knuth-Morris-Pratt, and the Aho-Korosik. However, we will only give out the implementation of the Rabin-Karp. So let's get started with Rabin-Karp. In 1987, Richard M. Karp and Michael O. Rabin proposed a string matching algorithm that performs well in practice and generalizes string matching against a set of patterns. The Rabin-Karp algorithm takes big O of m time in its pre-processing stage, and its worst-case running time is big O of n minus m plus 1 times m, very similar to Boyer-Moore's. In the highlighted code, you see an implementation of the Rabin-Karp algorithm for matching a string from a set of alphabetical characters that has decimal digits. In order to do this, the first thing is to convert the text and pattern strings into digits. Then, we'll need to use if and for loops to calculate the number of matching characters. The highlighted code shows the pre-compute part of the algorithm. In the for loop at the end of this highlighted code, you see long variables ph and th being equal to the character after the conversion. Below that, you see the for and if loops that will calculate the number of matching characters. The Knuth-Morris-Pratt, or KMP algorithm, is a single pattern string searching algorithm conceived by Donald Knuth and Von Pratt in 1970, and independently by James H. Morris, being jointly published by the three in 1977. When compared to the Boyer-Moore algorithm, KMP employs the observation that when a mismatch occurs, the pattern embodies sufficient information to determine where the next match could begin. It is similar to the Boyer-Moore in the sense that it efficiently skips unnecessary comparisons. The KMP algorithm has a running time of big O of n. The Aho-Korosik algorithm is a string searching algorithm invented by Alfred V. Aho and Margaret J. Korosik. Similar to the extended version of the Rabin-Karp algorithm, it is capable of matching elements of a dictionary, a set of words, with an input text. The idea behind it is to build a finite state machine that enables matching all strings of the dictionary simultaneously. The algorithm is linear in the length of the strings plus the length of the search text plus the number of output matches. If n is the length of the searched text, m is the sum of the length of all words in the dictionary, and z is the total number of occurrences of words in the text. Therefore, the time complexity of the Aho-Korosik algorithm is big O of n plus m plus z. In this lesson, we've introduced the string matching problem. We've started from the naive search algorithm and improved it by using the rules introduced by Boyer and Moore. We've seen how these rules improve the average runtime complexity of our algorithm. We've also explored some other string matching algorithms without going into too much detail about them. In the next topic, we'll be exploring graphs and their applications. Welcome to Lesson 6, Graphs, Prime Numbers, and Complexity Classes. Graph problems are very common in computer science, and their applications pervade many real-life applications. Everything that can be represented by entities and their relationships can ultimately be modeled by a graph. How we connect with friends on social media, how route planning applications are able to find the shortest route, and how e-commerce websites are able to provide us with recommendations are all examples of problems modeled by graphs. This lesson has 5 topics. Topic A, representing graphs. Topic B, traversing a graph. Topic C, calculating shortest paths. Topic D, prime numbers and algorithms. And lastly, Topic E, other concepts in graphs. By the end of this lesson, you will be able to explain the common problems associated with graphs, write an algorithm to compute prime numbers up to a certain limit, list different applications of graphs, and lastly, identify different complexity classes of problems. As an introduction, a graph is a structure composed of a set of objects in which some pairs of objects are related. The objects are modeled by the mathematical abstraction of vertices, sometimes also called nodes, and the pairwise relationships are modeled by the mathematical abstraction of edges, sometimes also called arcs. Edges can be directed or undirected. A directed edge is an edge which has a direction associated with it. A graph that is composed of directed edges is called a directed graph. A graph that is composed of undirected edges is called an undirected graph. In a directed edge, it is common to call the start of the edge the head and the end of the edge the tail. In a directed graph, the out degree of a vertex is the number of edges whose head is adjacent to it. Lastly, the in degree of a vertex is the number of edges whose tail is adjacent to it. Below are examples of directed and indirected graphs. First, the directed graph, and second, the indirected graph. Do you see the difference? Before we dive into how to represent a graph in a computer program, it is important to describe how the runtime of graph algorithms is usually characterized. As previously stated, a graph G can be seen as a set of vertices and edges, that is, G equals VE. As such, the size of the input is usually measured in terms of the number of vertices and the number of edges. So instead of relying solely on input size, the runtime of graph algorithms usually refers to both V and E. In big O notation, it is common to use V to denote V and E to denote E. For example, an algorithm that runs in time proportional to the number of vertices multiplied by the number of edges is said to run in time big O of VE. Now on to Topic A, representing graphs. A data structure that gives us the ability to insert, search, and optionally delete elements in a collection is called a data dictionary. Commonly, the type of data used is a key-value pair association, where we insert the key-value pair, but search using a key to obtain the value. Hash tables provide us with a fast data structure for organizing these key-value pairs and implementing our data dictionary. They are useful in a wide variety of applications due to the quick lookup and ease of use for in-memory data storage. Insertion and search operations have a typical average runtime complexity of big O of 1. There are usually 2 standard ways to represent a graph G equals VE in a computer program. 1 as a collection of adjacency lists, and 2 as an adjacency matrix. You can use either way to represent both directed and undirected graphs. We'll start by looking at the adjacency list representation. The adjacency list representation of a graph consists of an array of V lists, one for each vertex in V. For each vertex U in V, there's a list containing all vertices V so that there is an edge connecting U and V in E. This figure shows the adjacency list representation of the directed graph. For undirected graphs, we follow a similar strategy and build the adjacency list as if it were a directed graph with 2 edges between each pair of vertices, U and V, which are UV and VU. This figure shows the adjacency list representation of the undirected graph. If G is a directed graph, the sum of the lengths of all the adjacency lists is E edges, as each edge constitutes a single node of one of the adjacency lists. If G is an undirected graph, the sum of the lengths of all the adjacency lists is 2 times E, since each edge, U, V, appears twice. That is, once in U's and once in V's adjacent list. For both types of graphs, the adjacency list representation has the property of requiring an amount of memory equal to big O of V plus E. The following code snippet shows how to create a graph using the adjacency list representation in Java. It is common for one to have weighted graphs. That is, graphs in which each edge has an associated weight. The adjacency list representation is robust enough to support different graph variants, since we can store different edge representations in the adjacency lists. Of note, we can store different edge representations in adjacency lists because we store the edges themselves, thereby allowing customizable representations. In order to implement adding weights to the directed graph, we need to adapt the implementation of the adjacency list graph class to support weights on the edges. This adjacency list graph class is before you, and here we see an adjacency that equals a new array list, and on each loop of the nodes, we simply create a new edge. Now if we go to the weighted graph, we see a different implementation. Not only have we added the edge, but we've added its weight. This can be seen in line 25. The adjacency list representation of a graph provides a compact way to represent sparse graphs, for example, those for which E is much less than V squared. Even though it is a representation that is useful for a lot of algorithms, which we will visit later, it does not support some features. For example, one cannot quickly tell whether there is an edge connecting two given vertices. In order to determine if U and V are connected, one has to go through the adjacency list of U to find an edge connecting it to V. Since the adjacency list of U can have at most E edges, this procedure runs in big O of E time. One alternative representation that remedies this disadvantage at the cost of using asymptotically more memory is the adjacency matrix representation. In this representation, a graph G equals VE is represented by a V times V matrix A, Aij, where Ij equals 1 if there's an edge Ij and 0 otherwise. The following table shows the adjacency matrix representation of the directed graph. The following table shows the adjacency matrix representation of the undirected graph. The adjacency matrix representation of a graph requires big O of V squared memory, independent of the number of edges in the graph. One thing to note on the adjacency matrix representation of undirected graphs is that the matrix is symmetrical along the main diagonal, since UV and VU represent the same edge. As such, the adjacency matrix of an undirected graph is its own transpose, A equals AT. Taking advantage of this symmetry, one can cut on the memory needed to store the graph almost in half, as you don't need the array of each vertex to have size V. If I tracks the index of vertices in V, the size of the array can decrease by 1 as I increases by 1. The following code shows how to create a graph using the adjacency matrix representation in Java. Of note, you can visit this link to access the code. The adjacency matrix representation is also robust enough to support different graph variants. In order to support weighted graphs, for example, one can store the weight of the edge in Aij instead of just 1. The adjacency list representation is asymptotically at least as space efficient as the adjacency matrix representation. But adjacency matrices are simpler, so they might be preferable when the graphs are reasonably small or dense. As previously stated, a sparse graph is one in which E is much less than V squared, whereas a dense graph is one in which E is closer to V squared. The adjacency list representation is more memory efficient for sparse graphs. For dense graphs, an adjacency matrix representation is better suited, as it possibly takes less memory due to list pointers. Now on to topic B, traversing a graph. A common activity on a graph is visiting each vertex of it in a given order. We will start by introducing the breadth first search and then follow with the depth first search. Both of these techniques form the archetype for many important graph algorithms, as we will see later with the cycle detection and Dijkstra's algorithm for single source shortest paths. Given a graph G equals VE and a source vertex S, breadth-first search explores the edges of G systematically to discover every vertex that is reachable from S. While doing so, it computes the smallest number of edges from S to each reachable vertex, making it suitable to solve the single source shortest path problem on unweighted graphs, or graphs whose edges all have the same weight. Breadth-first searches, BFS, is named so because it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of that frontier. In that sense, the algorithm first explores vertices at distance k from S before discovering vertices at distance k plus 1. To keep track of progress, breadth-first search identifies each vertex as undiscovered, discovered, or expanded. All vertices start out undiscovered. A vertex is discovered the first time it is encountered during search, and is expanded when all vertices adjacent to it have been discovered. BFS constructs a breadth-first tree rooted at source vertex S. Whenever the search discovers an undiscovered vertex V, when scanning the outward edges of already discovered vertex U, the vertex V and the edge UV are added to the tree. Therefore, U becomes the parent of V in the breadth-first tree. Since a vertex is discovered at most once, it has at most one parent. In order to illustrate this, let's look at a run of breadth-first searches for the directed graph, starting at node 2 in the following table. Remember, breadth-first searches are named because they expand the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. So in our first step, we start with the initial node 2. There's nothing expanded, and there are 5 nodes to be discovered that are right now undiscovered. Our tree exists solely of the current node 2. In step 1, we move down to the 4th node, and at this point, nodes 2 and 5 are discovered, and we've expanded off 2, leaving 0, 1, and 3 to be discovered because they're undiscovered. Then we have step 2, and the current node will be 5. At this point, nodes 2, 4, 5, and 3 are all discovered, 2 and 4 are expanded, and 0 and 1 are left undiscovered. Let's keep going. In step 3, we have our current node of 3, and now all are discovered, 2, 4, and 5 are expanded, and none are left undiscovered. We go to step 4, the current node is 1, all are discovered, all but 1 are expanded, and 0 are undiscovered. And in our final step, step 5, our current node is null, and we've discovered all and expanded all, and none are left undiscovered. There are a lot of insights to take from the breadth-first tree. For instance, the path from the root to a given node in the tree is the shortest path in terms of edges from those 2 vertices. Another thing to note is that vertices that are not in the breadth-first tree, as is the case of 0, are unreachable from the root vertex. We previously saw how to perform the breadth-first search on trees. BFS on graphs is similar, but we need to keep track of explored nodes so that we don't get stuck in cycles. In order to implement breadth-first search, we will assume that our graph is represented using adjacency lists. We will attach certain attributes to each vertex in the graph that will allow us to guide our search and later construct the breadth-first tree. We will also use a first-in, first-out queue, which we covered in Lesson 2, where we sorted algorithms and fundamental data structures to manage the set of discovered vertices. The following code snippet illustrates the implementation of the breadth-first search. Here we have an integer q that equals a new link. Let's focus on the implementation of the BFS function. We start by initializing a couple of auxiliary arrays, parent and visited. The first one will hold at parent I, the parent of node I, in the breadth-first tree. The second one will tell us at visited I whether or not vertex I has been discovered. We start by discovering the starting node and adding it to a queue. The queue will keep those vertices that have been discovered but not yet expanded. As such, while there are still elements in the queue, we will take this first element, go through its adjacent vertices, and discover those that haven't already been discovered, adding them to the queue. When the queue becomes empty, we're sure of having expanded all vertices that are reachable from the starting vertex. In the previous implementation, we've returned the array of parent nodes of the breadth-first tree in the BFS function, allowing us to reconstruct the paths. If not necessary, You could just return the size of the paths or any other information we might be interested in extracting from the breadth-first search traversal. In the BFS method, we're sure of enqueuing and hence dequeuing each vertex at most once. As such, the total time dedicated to queue operations is big O of V. After dequeuing each vertex, we scan its adjacency list. Since we dequeue each vertex at most once, we scan each adjacency list at most once. As the sum of lengths of all the adjacency lists is big O of E, the total time spent in scanning adjacency lists is big O of E. Therefore, the BFS procedure has an initialization time of big O of V and a total running time of big O of V plus E, running in linear time to the size of the adjacency list representation of G. As we will see in later topics, the BFS procedure is the archetype for many important graph algorithms. Given a graph G equals VE and a source vertex S, depth-first search explores the edges of the graph by going deeper in the graph whenever possible. Depth-first search, or DFS, explores edges adjacent to the most recently discovered vertex V that still has unexplored edges whose head is adjacent to it. Once all of these edges have been explored, the search backtracks to explore edges, leaving the vertex from which V was discovered. The process continues until all vertices that are reachable from the original source vertex have been discovered. If any undiscovered vertices remain, then DFS selects one of them as it repeats the search from that source. While it may seem odd that BFS limits itself to vertices reachable from a single source, whereas DFS considers multiple sources, the reason behind it is related to the applications of these searches. BFS is usually used to find shortest path distances, while DFS is often used as a subroutine in another algorithm, which we shall see when we explore the cycle detection problem. In order to illustrate this, let's look at a run of DFS for the directed graph starting at node 2 in the following table. Step 0, our current node is 2, we've discovered 2, expanded nothing, and 5 nodes are left undiscovered. Of course, our forest at this point is node 2 only. When we go to step 1, current node now is 4, we've discovered both 2 and 4, again nothing is expanded, and 4 nodes 0, 1, 3, and 5 are left undiscovered. And in step 2, our current node is 3, we've now discovered 2, 4, and 3, we've expanded nothing, and now there are only 3 nodes left undiscovered, 0, 1, and 5, and now our forest exists with 2, 4, and 3. Now for step 4. Step 4, we have our current node of 3, 4 nodes have been discovered, 1 expanded now, and 0 and 5 are left undiscovered. And in step 5, our current node is 4, we've discovered 2, 4, 3, and 1 again, but yet now expanded 1 and 4. We've left 0 and 5 undiscovered. Let's take it a bit further. In step 6, we have current node of 2, we've discovered 4, expanded 1, 4, and 3, and now 0 and 5 are undiscovered. So we're cycling through a subroutine. In step 6 again, current node is now 5, all 5 nodes are discovered, we have 2, 4, 3, 1, and 5, we've expanded 1, 4, and 3, and 0 is undiscovered. And in step 7, we have current node of 2, 5 discovered, 4 expanded, and our forest has grown. Now let's look at our final 2 steps, 8 and 9. In step 8, we have a 0 current node, everything's discovered. Expanded is 1, 4, 3, 5, and 2, and nothing is left to be undiscovered. In step 9, our current node is now null. Our forest is full, we've discovered everything, and we've expanded everything. Note that the results of DFS may depend on the order in which the vertices are examined. In the previous case, we started with 2 and always went for the lowest numbered vertex in the adjacency list of a vertex first. If we had started with vertex 0, we would have had a different forest. In practice, we can usually use any DFS result with equivalent results. We previously saw how to perform DFS on trees. DFS on graphs is similar, but we need to keep track of explored nodes so that we don't get stuck in cycles. In order to implement DFS, we will assume that our graph is represented using adjacency lists. We will attach certain attributes to each vertex in the graph, which will allow us to guide our search and later construct the depth-first forest. The following code snippet illustrates the implementation of depth-first search. The DFS procedure works by initializing all vertices as not visited and setting their parents to -1. This means that they have no parent. Then we find the first undiscovered vertex and visit it. In each visit, we start by recording the vertex as visited, and then going through its adjacency list. There, we are looking for vertices not yet discovered. Once we find one, we visit it. Looking at the previous implementation, we see that the loops inside DFS take time big O of V as they run for each vertex in the graph. We also can see that the DFS visit method is called exactly once for each vertex. During the execution of DFS visit method, the loop scanning the adjacency list executes in time proportional to the size of the vertex's adjacency lists. Since we said before that DFS visit method is called exactly once for each vertex, the total time spent in the loop is proportional to the sum of the sizes of all adjacency lists. A useful application of DFS is determining whether or not a graph is acyclic. That is, it does not contain cycles. In order to do so, it's important to define 4 types of edges in terms of the depth-first forest produced by DFS. They are as follows: tree edges, back edges, forward edges, and cross edges. With tree edges, they are edges in the depth-first forest. An edge can only be a tree edge if it was the one explored when first discovering a vertex. With back edges, they are edges connecting a vertex to an ancestor in a depth-first tree. Self-loops, which may occur in directed graphs, are back edges. Forward edges, they are edges that do not belong to a depth-first tree, but connect a vertex to one of its descendants in a depth-first tree. Forward edges are therefore edges that weren't used when performing the DFS, but connect vertices U and V in a depth-first tree provided that V is a descendant of U in the tree. And cross edges, they are all other edges. They can go between vertices in the same depth-first tree, or they can go between vertices in different depth-first trees. They are therefore edges that weren't used when performing the depth-first search, but connect vertices that don't share an ancestor relationship in the same tree, or vertices in different trees. Having classified edges, it is possible to show that a directed graph is acyclic if and only if a DFS does not produce back edges. If a depth-first search produces a back edge, UV, then vertex V is an ancestor of vertex U in the depth-first forest. Therefore, G contains a path from V to U, and UV completes a cycle. The algorithm is generalizable for undirected graphs. In undirected graphs, we find a back edge, UV, and V is not the parent of U in the depth-first forest. Then we are in the presence of a cycle. The shortest path is a path between two vertices so that the sum of the weights of the edges that constitute the path is minimized. The shortest path problem has many applications in the real world, from finding directions on mapping applications to minimizing the moves to solve a puzzle. In this topic, we shall look at 2 different strategies for computing shortest paths. One that finds the shortest paths from a single source to every other vertex in the graph, and another that finds the shortest paths between all pairs of vertices in a graph. When we explored BFS, we saw that it was able to solve the shortest path problem for unweighted graphs, or graphs whose edges have the same positive weight. But what if we are dealing with weighted graphs? Can we do better? We shall see that Dijkstra's algorithm provides an improvement over the ideas presented in BFS, and that it is an efficient algorithm for solving the single source shortest path problem. One restriction for working with Dijkstra's algorithm is that the edges' weights have to be positive. This is usually not a big issue since most graphs represent entities modeled by edges with positive weights. Nonetheless, there are algorithms capable of solving the problem for negative weights. Since the use case for negative edges is less common, those algorithms are outside the scope of this course. Dijkstra's algorithm, conceived by Edgar Dijkstra in 1956, maintains a set of S vertices whose final shortest path weights from the source S have already been determined. The algorithm repeatedly selects the vertex U with the minimum shortest path estimate, adds it to set S, and uses the outward edges from that vertex to update the estimates from vertices not yet in set S. In order to see this in action, let's consider a sample weighted direct graph. The graph is composed of 5 vertices, A, B, C, D, and E, and 10 edges. We're interested in finding the shortest paths, starting at vertex A. Note that A is already marked as 0, meaning that the current distance from A to A is 0. The other vertices don't have distances associated with them yet. It is common to use an estimate of infinity as the starting estimate for the distance of nodes not yet seen. The following table shows a run of Dijkstra's algorithm for the graph, identifying the current vertex being selected and how it updates the estimates for vertices not yet seen. In the first step, we see vertex A is the vertex with the lowest estimate weight, so it is selected as the next vertex whose edges are to be considered to improve our current estimates. And in the second step, we can use the outward edges of vertex A to update our estimates for vertices B and D. Afterwards, we can add A to set S, avoiding a repeated visit to it. From the edges not yet visited, the one with the lowest estimate is now D, which shall be selected to visit next. Note that we also mark these edges that belong to our estimate, shortest path, in bold. The following table shows a run of Dijkstra's algorithm, identifying the current vertex being selected and how it updates the estimates for vertices not yet seen. In the first step, by exploring the outward edges from vertex D, we were able to improve our estimate for vertex B, so we updated accordingly and now consider a different edge for the shortest path. We were also able to discover vertices C and E, which now become potential candidates to visit next. Since E is the one with the shorter estimate weight, we will visit it next. In the next step, using an outward edge from vertex E, we were able to improve our estimate for vertex C, and now look at vertex B as our next vertex to visit. The vertices that belong to set S already have their shortest path computed. The value inside them is the weight of the shortest path from A to them, and you can follow the edges in bold to build the shortest path. The following table shows a run of Dijkstra's algorithm, identifying the current vertex being selected and how it updates the estimates for vertices not yet seen. In step 1, we see that from vertex B, we were able to once again improve our estimate for the shortest path to vertex C. Since vertex C is the only vertex not yet in set S, it is the one visited next. And in the next step, since vertex C has no outward edges to vertices not yet in S, we conclude the run of our algorithm and have successfully computed the shortest paths from A to every other vertex in the graph. Now that we've seen a run of Dijkstra's algorithm, let's try to put it in code and analyze its runtime performance. We will use an adjacency list representation for our graph, as it helps us when trying to explore the outward edges of a given vertex. The following code snippet shows a possible implementation of Dijkstra's algorithm as previously described. The Dijkstra method starts by initializing two sets, one for visited vertices and one for unvisited vertices. We can see that in lines 65 and 66. The set of visited vertices corresponds to the set we previously named as S, and we use the one of not visited vertices to keep track of vertices to explore. We then initialize each vertex with an estimated distance equal to integer.max_value, line 70. This represents the value of infinity for our use case. We also use a parent array to keep track of parent vertices in the shortest path, so that we can later recreate the path from the source to each vertex. The main loop runs for each vertex, while we still have vertices not yet visited. For each run, it selects the best vertex to explore. In this case, the best vertex is the one with the smallest distance of the vertices not visited so far. The getBestEstimate function simply scans all vertices in the not visited function set for the one satisfying the requirement. Then it adds the vertex to the set of visited vertices and updates the estimated distance for not visited vertices. When we run out of vertices to visit, we build our paths by recursively visiting the parent array. Analyzing the runtime of the previous implementation, we can see that we have an initialization step that's proportional to the number of vertices in the graph, hence running in big O of V. The main loop of the algorithm runs once for each vertex, so it is bounded by at least big O of V. Inside the main loop, we determine the next vertex to visit and then scan its adjacency list to update the estimate distances. Updating the distances takes time proportional to big O of 1, and since we scan each vertex's adjacency list only once, we take time proportional to big O of E, updating estimated distances. We're left with the time spent selecting the next vertex to visit. Unfortunately, the getBestEstimate method needs to scan through all the unvisited vertices. and is therefore bounded by big O of v. The total running time of our implementation of Dijkstra's algorithm is therefore big O of v squared plus e. Even though some parts of our implementation seem difficult to optimize, it looks like we can do better when selecting the next vertex to visit. If we could have access to a data structure that was capable of storing our vertices sorted by lower estimated distance, and provided efficient insert and remove operations, then we could reduce the big O of v time spent inside the get best estimate method. In Lesson 4, Algorithm Design Paradigms, we briefly discussed the data structure used in Huffman coding, named the priority queue, which is just what we need for this job. In this code snippet, the highlighted code implements a more efficient version of Dijkstra's algorithm using a priority queue. In this second implementation, we no longer keep sets for visited and not visited vertices. Instead, we rely on a priority queue that will be storing our distance estimates while we run the algorithm. When we are exploring the outward edges from a given vertex, we therefore add a new entry to the priority queue in case we are able to improve our distance estimate. Adding and removing an element from our priority queue takes big O of log n time, n being the number of elements in the queue. Note that we can have the same vertex inserted more than once in the priority queue. That's why we check it if we visited it before expanding its edges. Since we will visit the instance for that vertex with shorter estimate distance, it's safe to ignore the ones that come after it. However, that means that operations on our priority queue are not bounded by big O of log v, but big O of log e instead, assuming that there's a connected graph. Therefore, the total runtime of this implementation is big O of v plus e times log e. It's still possible to improve this running time by using a priority queue implementation with a better asymptotic bounds, such as a Fibonacci heap, but its implementation is out of the scope of this course. Sometimes it might be necessary to compute the shortest paths between all pairs of vertices. For example, we might be interested in building a table of distances. One way to do that is to perform a single source shortest path for every vertex of the graph. If you use Dijkstra's algorithm for that, we end up with a runtime of big O of v times v plus e log e. In this subtopic, we shall explore an algorithm capable of solving the all pairs shortest paths problem in big O of v to the third time, with a remarkably simple and elegant implementation. The algorithm we are about to study, more commonly referred to as the Floyd-Warshall algorithm, was first published in its current form by Robert Floyd in 1962. However, in its essence, it follows the same ideas published by Bernard Roy in 1959 and Stephen Warshall in 1962. The algorithm uses the adjacency matrix representation and follows a dynamic programming approach. The basic idea behind it is that when we're trying to compute the shortest path distance between vertex I and vertex j, we try to use an intermediate vertex k. We want to use an intermediate vertex so that doing the path from I to k, and then from k to j, shortens the currently computed shortest path between I and j. If we find such a vertex, then the best path we're able to compute so far between I and j must go through k. All that we need to do is, for each k, see if using it improves the shortest path between I and j for all possible I and j. In order to see that in practice, let's use the directed graph that we used to illustrate Dijkstra's algorithm. The graph has the adjacency matrix representation of the following table. The adjacency matrix representation serves as the starting point for the Floyd-Warshall algorithm, and we iterate through it until we're left with a matrix of the weights of the shortest paths between each pair of vertices. In order to do so, let's start with vertex A, considering it as an intermediate vertex for shortest paths. Unfortunately, vertex A doesn't always have inward edges, meaning that it can't be used as an intermediate vertex for shortest paths. Using vertex B, we can improve the distance from A to C, 10 plus 1 is less than infinity, and we can use it to go from A to D, but not improve the overall distance. We can also use it to improve the distance from D to C, which is 3 plus 1 is less than 9. Therefore, after considering B as an intermediate vertex, we're left with the distance matrix of the following table. Now we are going to look at vertex C. Using vertex C, we can improve the distance from A to E of 11 plus 4 less than infinity, and B to E of 1 plus 4 less than infinity. Using vertex D, we can improve the distance from A to B, or 5 plus 3 less than 10. A to C, 5 plus 4 less than 11, A to E, 5 plus 2 less than 15, and B to E, 2 plus 2 less than 5. And using vertex E, we cannot improve any distance. Implementing the Floyd-Warshall algorithm is very simple, as the following code snippet demonstrates. Looking at the implementation, the runtime of big O of v to the third becomes obvious. One alternative to the Floyd-Warshall algorithm is running Dijkstra's algorithm for each vertex in the graph, so that we end up with all pairwise shortest paths. Given that its complexity is closer to multiple applications of Dijkstra's algorithm for dense graphs, the Floyd-Warshall algorithm is frequently used in practice. Now let's dive into topic D, prime numbers and algorithms. Here's where we'll learn about prime numbers and how to write an algorithm about whether to find out whether a given number is prime or not. A prime number is a natural number greater than one whose only divisors are 1 and the number itself. Prime numbers play a very important role in the fundamental theorem of arithmetic. Every natural number greater than 1 is either a prime or a product of primes. Nowadays, number theoretic algorithms are widely used, mainly due to cryptographic schemes based on large prime numbers. Most of those cryptographic schemes are based on the fact that we can efficiently find large primes, but we cannot factor the product of those large primes efficiently. The sieve of Eratosthenes is a simple and ancient algorithm to find all prime numbers up to a given limit. If we want to find all prime numbers up to n, we start by creating a list of consecutive integers from 2 to n, like 2, 3, 4, 5, all the way up to n, initially unmarked. Let's use p to denote the smallest unmarked number. Then we select the smallest unmarked number p that is larger than the last p. In the first iteration, p will be 2. Afterwards, by increments of p, we mark elements in the list from 2p until mp so that mp is less than or equal to n. We repeat this strategy until it is impossible to mark more numbers in the list. At the end of the run, all the unmarked numbers are prime numbers. It is easy to see that all unmarked numbers will be the ones for which we couldn't find a divisor other than the number itself and 1, and are therefore prime numbers. Prime factorization is determining the prime factors of a given number. It is very difficult to build a general-purpose algorithm for this computationally hard problem. A general-purpose algorithm that is commonly used to factorize primes was introduced in Lesson 1, Algorithms and Complexities. Its basic idea is to iterate through possible factors attempting to divide the number. We start with 2. While the number is divisible by 2, we keep dividing it and add 2 to the list of factors. Afterwards, the number must be odd, so start a loop that checks for possible factors from 3 to the square root of the number. Since we've already covered even numbers, you can do increments of 2 in this loop. There's no need to check 4, 6, 8, and so on once you've already checked 2. Once you find a suitable divisor, add the number to the list of factors and divide it until it is possible. At the end of this step, if we are left with a number greater than 2, then it is a prime number and therefore a prime factor of itself. In this lesson, we covered ways of representing and traversing a graph and looked at shortest path algorithms. Graphs are also an optimal data structure for some problems we haven't mentioned yet. This topic aims to introduce some of them. A minimum spanning tree of a graph is a subset of the set of edges E of a connected graph that connects all vertices together without any cycles and with the minimum total edge weight. It is a tree because every 2 vertices in it are connected by exactly one path. In order to understand the applicability of minimum spanning trees, consider the problem of a telecommunications company that is moving into a new neighborhood. The company wants to connect all the houses, but also wants to minimize the length of cable that it uses in order to cut costs. One way to solve the problem is by computing the minimum spanning tree of a graph whose vertices are the houses of the neighborhood, and the edges between houses are weighted according to the distance between them. There are many algorithms to solve the minimum spanning tree problem. Two of the most famous are Prim's and Kruskal's. Prim's algorithm is a greedy algorithm that repeatedly selects the edge of smaller weights that connects some edge not yet in the spanning tree with some edge already in the spanning tree. Its runtime depends on the implementation, but it's possible to achieve a runtime of big O of V log E. It can be implemented similarly to Dijkstra's algorithm. We start with one vertex chosen arbitrarily to be part of the tree. All edges that connect to this starting vertex are added to a set of candidate edges that are sorted according to the edge's weights. While we still have vertices to add to the tree, we repeatedly select the edge with the smaller weight from the list of candidate edges that connects to a new vertex not yet in the tree, and then we repeat the process for the new vertex. Kruskal's algorithm is also a greedy algorithm that uses a disjoint set data structure. A disjoint set data structure, or union-find data structure, is a data structure that tracks elements that are partitioned into a number of non-overlapping subsets. It provides an efficient way to merge two sets and check whether two elements belong to the same set. The idea of Kruskal's algorithm is to reduce a forest, for example a set of trees, to a single tree, using a disjoint set data structure to keep track of trees. We start with one tree for each vertex, including only one vertex. While we have more than one tree, we select the edge of the smallest weight that connects two different trees. We don't want to produce a cycle, and then we join the two trees together. At the end, the resultant tree will be the one whose total edge weight is minimized. The running time of Kruskal's algorithm is also big O of V log E. The A-star search algorithm is a very common algorithm when solving pathfinding problems. It also solves the shortest path problem, enhancing Dijkstra's algorithm with the introduction of a heuristic to guide the search. A heuristic is a practical estimate of a given cost, not guaranteed to be optimal or perfect, but sufficient for the immediate goals or to guide a search. Its basic idea is that when adding this heuristic to the estimated distance already computed for a node, one can guide the search towards the goal and avoid visiting certain vertices. For example, if we use the Euclidean distance, for example the straight line distance between 2 points, from our location to the exit of a given maze, we can guide the search toward that and avoid visiting certain unnecessary positions. Of note, the squares marked with an X are not explored in the A-star search if we're using a good heuristic. Some directed weighted graphs can be seen as flow networks. In a flow network, edge weights represent capacities, and each edge receives a flow that can't exceed the edge's capacity. The maximum flow attempts to find a feasible flow through the network that is maximum, considering a single source, where the initial flow starts, and a single sink, where the flow ends. The maximum flow problem allows one to solve related problems like pairwise assignment. There are various algorithms to solve the maximum flow problem. Of note, the labels on the edges represent the used and total capacity of the edge. Three of the most famous ones are the Ford-Fulkerson algorithm, the Edmonds-Karp algorithm, and Dinich's algorithm. The idea behind the Ford-Fulkerson algorithm is to repeatedly find augmenting paths in the flow network. An augmenting path is a path that still has an available capacity. While it is possible to find augmenting paths, one can add a flow through the path equal to its capacity and repeat the process. Ford-Fulkerson algorithm runs in big O of E times F, where F is the maximum flow of the graph. The Edmonds-Karp algorithm improves on the Ford-Fulkerson algorithm by always selecting the augmenting path that is the shortest. The runtime complexity of the Edmonds-Karp algorithm is big O of V times E squared, independent of the maximum flow value. Dinich's algorithm runs in big O of V squared times E time, also building on shortest augmenting paths, but uses some concepts that make it more suitable for sparse graphs. Nearly all of the algorithms introduced so far run in polynomial time. For instance, on inputs of size n, their worst case running time is big O of n to the k power for constant k. However, there are problems that simply cannot be solved or for which a polynomial time algorithm hasn't been found yet. An example of a problem that cannot be solved is the halting problem. The halting problem is the problem of determining from the description of a computer program and an input whether the program will finish running or continue to run forever. Alan Turing proved that a general algorithm to solve the halting problem for all pairs of program and input cannot exist. It is common to call problems solvable by polynomial time algorithms, for instance those whose worst case running time is big O of n to the k power for constant k, as tractable or easy, and problems that require a super polynomial time algorithm, for instance those whose running time is not bounded above by any polynomial, as intractable or hard. There is a class of problems called NP-complete or NPC problems, and no one has yet found a polynomial time algorithm to solve them. However, no one has yet been able to prove that no polynomial time algorithm can exist for any of them. There is another class of problems called NP problems, whose solutions are verifiable in polynomial time. This means that, given a problem and a possible solution to it, one can verify if the solution is correct in polynomial time. All problems in P are also in NP. NPC consists of problems that belong to the NP class and to the NP hard class. A problem is NP hard if an algorithm for solving it can be translated into one for solving an NP problem. One of the deepest open research problems in theoretical computer science is whether P is really different from NP. For example, P not equal to NP. Examples of NPC problems are as follows: finding the longest path in the graph, or finding a path in a graph that visits all vertices exactly once, known as a Hamiltonian path. A common example of an NP hard problem is finding the shortest path in a graph that visits all vertices exactly once and returns to the starting point. The problem consists of finding the Hamiltonian cycle of the smallest weight and is often described as the traveling salesman problem, as it models the problem of a salesman that needs to visit all cities and return to his hometown. In this lesson, we have introduced graphs, formalized what they are, and shown two different ways of representing them in computer programs. Afterwards, we took a look at ways of traversing graphs, using them as building blocks for building more complex algorithms on top. Then we looked at two different algorithms for finding shortest paths in a graph. We have briefly explored topics that logically follow the ones studied in this course. Even though they haven't been explored at a great level of detail, this lesson gives pointers for curious students to study on their own after these 2 days. The world of data structures and algorithms is vast and requires a type of mathematical reasoning for which some study and practice is required. However, one of the most rewarding feelings in the life of a software engineer is coming up with a clever algorithm to solve a hard problem.